Okay, so good morning, everyone, on this morning session of our Thursday, where we will conclude the general session by three talks that promise to be very interesting. And so, first of all, we will have M.N.Hounkonnou from the Faculty of Mechanical Engineering of the University of Niš, who will be giving her talk entitled Constructive Semigroups Better Partners, the Theory, Development and Applications. So, Melanija, please.
Thank you very much, Igor. Last part of a general session of our conference is dedicated to the theory of constructive semigroup with the partners. On the behalf of our small group, which have been working on the topic during last couple of years, I'm going to talk about theory development and applications. As it is well known in classical mathematics, in classical semigroup theory, the order theory provides one of the most basic tools of semigroup theory within, of course, this setting. In particular, the structure of semigroups is usually most clearly revealed through the analysis of the behavior of the appropriate orders. Having this in mind, we put a lot of attention to develop an appropriate constructive order theory for semigroup with the partners. In continuation after me, Eric Darpo will talk about our results on the co-transitive kernel of a relation in constructive semigroup theory, and Marian Alexandru Baroni will present our results on positive weak co-quasi-order on semigroups. Inspired by results obtained in interactive theorem proving the approach of formal verification, we develop a new constructive algebraic theory known as a theory of semigroup with the partners. A descriptive definition of semigroup with the partners includes two main parts. The notion of a certain classical algebraic structure is straightforwardly adopted. The structure is equipped with n partners with the corresponding multiplicative operation. This talk aims to provide a clear and understandable picture of constructive semigroups with the partners in Bishop style, both to classical algebraists and those who apply algebraic knowledge. The initial steps towards grounding the theory is done through our papers, which appeared in 2013 and 2016. In what follows, part of the results given in our recent paper here at the beginning, we will be presented. This talk has several purposes. To present the point of view of doing constructive algebra, our experience suggests that we are dealing with normal mathematical objects and we are working only with intuitionistic logic. To enable the audience to gain a better appreciation of the similarities and contrasts between classical and constructive semigroup theory, to lay a foundation for further works, to show that constructive semigroup with the partners are interesting in their own right, and what is more important, they can be fun and challenging. Theory of constructive semigroup with the partners is a new algebraic theory. Our theory is partially inspired by classical case, but it is distinguished from it in two significant aspects. Our work is based on the notion of partners. The reference given in the bottom of this slide suggests an interesting philosophical interpretation of intuitionistic logic. According to it, intuitionistic logic can be understood as the logic of scientific research. It was Hating who in the passage from classical theories to intuitionistic one, by deleting law of excluded middle, there is a choice of the right notions. Usually, but not always, the strongest notion fare best. Conversely, when passing from intuitionistic theories to classical ones by adding laws of excluded middle, usually a lot of notions are collapsed. It was Hayting who wrote in his famous book from 1956 that in order to build up a definite branch of intuitionistic mathematics, it is necessary in the first place to have a thorough knowledge of the corresponding branch of classical mathematics, and in the second place to know by experience where the intuitionistic pitfalls lie. Furthermore, following Bishop, at least initially, classical mathematics is seen as a guide that helps the constructive mathematicians develop new mathematics. Paraphrasing Wozni, modern algebra can be described in a couple of sentences. The story starts with sets and the relation on them and proceeds to the concept of a semigroup. And finally, very nice conclusion about our favorite structure. Semigroups serve as the building blocks for the structure comprising the subject which is today called modern algebra. So once again, Eric Bishop's style of constructive mathematics formed the framework for our work. The cornerstones of Bishop mathematics include the notion of positive integers, sets, and function. So, semigroup with a partners is a set with a partners with an associative and strongly extensional operation defined of it. Working within classical or constructive we're working within classical or intuitionistic logic. In order to analyze algebraic structure, it is needful to study other systems that are not algebraic structures. For example, set and other sets, relational system, etc. Contrary to the classical case, a set exists only when it is defined. What does it mean to define a set? You can see in the slide in front of you properties A and B, and set is inhabited if we can construct an element of S. The distinction between a non-empty set and an inhabited set is occurring in constructive set theory. From now on, our assumption is that our set is inhabited one. In constructive mathematics, one often needs stronger notion than the classical ones. A paradigm is the notion of inequality. There are different types of inequalities: denial inequality, apartness, tight apartness, to mention a few. Some of them completely independent, which only in classical mathematics are equal to one standard inequality. Apartness is the second most important relation in constructive mathematics. It is a binary relation which are irreflexive, symmetric, and co-transitive. If apartness and equality are connected in this way, such apartness is called tight apartness. Going to the literature, there are several variants of what is considered to be set with apartness, depending on the relation between equality and apartness defined on set. Our choice is, to a certain level, a novelty within constructive circles. We choose equality and apartness to be independent of each other, and our apartness is not in general tight one. Coming back to constructive algebra, it is more complicated than a classical in various ways. And up to now, there are 2 monographs published on the topics, and both are given in front of you. More about the background and motivation coming from the classical semigroup theory, other constructive mathematics disciplines, and computer science can be found in the references which is given in the bottom of this slide. And just a remark connected to our the way how we write quantifiers. From that point of view, we use those 2 references. The existence of apartness relational structure often gives rise to an apartness relation on another structure. So, given 2 sets with apartness, it is permissible to construct a set of mappings between them. Of special interest, of special importance are the mappings, so-called strongly instantial mappings, which are connected to apartness in this way. Why so from the semigroup theory point of view? Because semigroup with apartness arise from strongly instantial mapping from a set to itself. So the apartness full transformation semigroup arise in this way. As example of the previous theorem, we prove constructive Cayley's theorem for semigroup with apartness, theorem 2 in front of us. The presence of apartness implies the appearance of different types of substructures connected to it. So, for a subset from now on, S means semigroup or set with apartness. So, just to point out this fact. For a given subset, we can define 2 its complements, apartness and logical one. In general, this inclusion can be strict. And the question which arises here, for which type of subset we have equality between its 2 complements? Using complements, we distinguish the following type of subset: detachable, strongly detachable, and quasi-detachable subset. And again, open question: is the list from this or that point of view important subsets of a set or semigroup apartness complete with this one given in front of you? So I'm not going to comment this because I think that more about intuitionistic logic and omniscience principle, very important principle equivalent to low excluded middle, which are used in proving that certain statements from classical mathematics or whatever are not valid anymore in constructive settings. I will add this to Marian Baroni to explain us more. Right, Marian? Right, Marian? Right. Just a remark, in our small group, Marian is only native constructivist. But he will explain that more in his talk. So, in the relationship between detachable, strongly detachable, and quasi-detachable subset are completely described in the theorem in front of you. For example, SD subsets, and this subset are CUDI subset. For CUDI subset, we have two complements coincide, and unique complement is denoted on the following way. And again, a question, and very important result, not any subset of a semigroup or set with the partners is CUDI subset. Statement 6. So a number, it is known from classical semigroup theory that a number of subset of semigroups enjoy special properties relative to the multiplication. Those given in front of you shows in a constructive case as well. Completely isolated and convex subset can be found in the classical semigroup literature under different names. The names we used here are taken from the reference given at the very end of this slide. And co-subsemigroups and co-ideals are kind of mixture or taken from classical case and kind of mixture of subset which appear in the previous two slides, constructive and classical. Definition from Romano definitions from 1999. And one very important pitfall, status of power set within Bishop mathematics. It is questionable. The advice is avoided. The way of avoiding power set is one way is to work with a set of all mappings from a set to a set, and another way is to work with a well-defined but smaller set of subsets, whatever this means. And also important remarks that in general there is no natural partners relation for power set and quotient structure. Okay, we can go for them. Then it is also given to set with the partners. It is also permissible to construct the set of other pairs of those sets. And starting from this, more or less common definition from classical, more or less similar also from classical case, a binary relation is an inhabited set, subset of S cross set, S times S. So, of course, composition of operation defined on a set of relation on a given set or semigroups are one inherited from classical case, product, and one pretty new coproduct defined for constructive purpose. And very important question and distinction between classical semigroup theory and constructive semigroup theory from the very beginning. You're familiar with this, that two elementary examples of classical semigroup theory are a set of functions, mappings from a set to itself, and another is a set of binary relation on a given set under composition. What is the case here? We mentioned a partner's full transformation semigroup as an example, but what about relations? See, yes, it is very true that this operation is associative, but there is no way, or it is to define a partners on it, because, and in addition, let us remember one of the big pitfalls, status of power set. So, in addition, this relation is even not associative. Strongly reflexive and co-transitive relation are called co-quasi-order. Co-quasi-order are the main building block of order theory. We call it co-order theory, which we develop for the purpose of development of semigroup with partners. And one very important, very interesting property, if relation is, of course, important property is also this one, that co-quasi-orders could be subset of S times S, and that for them two complements coincide. Starting from a co-quasi-order, this unique complement is a quasi-order. And question again, what about vice versa relation? If we start from a quasi-order, is there a way to obtain is the quasi-order negation or complement logical or whatever of co-quasi-order? Let us analyze it. If relation is strongly irreflexive, or relation is strongly irreflexive if and only if it is its complement, the partner's complement at least, is reflexive. What about transitivity? It is known that complement of co-quasi-order of or co-transitive relation is transitive, but for the vice versa, it is not valid. So there is no way, it is not a general case, that the complement of any transitive relation is co-transitive. So big problem, and it is solved under certain pretty strong condition. For example, set has to be finitely enumerable, and relation has to be stable. But more about this and results, accompanying results to this very nice theorem, I assume we will have in Eric Darpot talks. So of course, quotient structure problem I mentioned is there is no natural partners in quotient structure. Quotient semigroup doesn't naturally inherit the partners from starting semigroup with the partners. So we cannot start with equivalence. This problem has the following algorithm. We start with coequivalence, then we proved that complements, it's logical, and a partner's complement coincide, of course, and that this complement is equivalence. Then, starting coequivalence, define the partners on a quotient structure. Important theorem in front of you for formulating and proving a partner's isomorphism theorems. One of them is given also in front of you. So, in our further development on our way, so how to find the constructive risk construction and how to find the constructive way, constructive risk congruence. Again, this is a very familiar facts from classical semigroup theory. Of course, the quotient semigroup is is semigroup here, but without apartness. Apartness is not naturally inherited. So again, to start to solve this problem, we start, of course, we need a notion of co-compatible relation, and co-congruence is now co-compatible co-equivalence. Co-equivalence is symmetric co-quasi-order. So to solve this problem, we start from a co-ideal. So we start from constructive notion. Constructive notion is here co-ideal. Its complement is an ideal of S. Using that ideal, we can define co-congruence. We can define Rees quotient semigroups. And we finally have this theorem. We defined co-congruence, accompanies co-congruence, and the final result describes construction of Rees quotient semigroups is in front of you, and constructive friend of Rees equivalence, congruence, I'm sorry. So, very important results. From which point of view important? See, trying to proving the converse of these, we reach to an extremely important point. How to say? Catching the fox, we caught the bear. So, first of all, this converse is not supported constructively, but as a consequence, very important fact, which is another evidence that our choice of set with the partners and equality completely independent we were completely right, because even if we start, it was proved that even if we start with tight apartness, with semigroup with tight apartness, Rees quotient semigroups is not a semigroup with tight apartness in general. So from very big point of view, very big, how to say, by past, we are often criticized why we are working, why we make such choice, why our partners and equality are independent, why when tighter partners work so well in so many areas, right, in so many areas. But here, recently, Eric and I got to the point of view that semigroup with tighter partners are not enough for this theory. Because if we start, once again, it is very important, if we start with Rees construction on a semigroup with the tighter partners, we can get Rees quotient semigroup to be semigroup with ordinary apartness. With apartness, it is not eventually tight. So, and here, green co-equivalences. Green co-equivalences, we put a lot of efforts to find constructive friends of Green's co-equivalence. You know, when we fight for our theory and a little bit history, some ideas were born, and the middle of 90s of last century, it was Romano who started with first definition and first results. Sometimes right, sometimes not, but it was pioneer work after all. Then in the beginning of 2000, Professor Cerenković joined the team. I was the last one. I joined the team in the middle of 2000. So when we prepared our first results, for example, our paper for 2013 for a publishing, there was a lot of rejecting. It was very interesting that when we sent this manuscript to some very known semigroup theoretician, but from classical semigroup theory, one of them, very respectable, says to us, people, you are not serious. You have nothing within your result about Green's relations, Green's equivalences. And that is right, said. You know, John Howe wrote, no one is serious introducing new class of semigroups without telling anything about Green's relation. Very true in classical semigroup theory. But imagine what? Semigroup with the partners are not new class of semigroups. Semigroup with the partners is new approach to semigroup theory. We posed that problem of finding kind of Green's co-equivalences, constructive friends in the very beginning, but even now when we have some results, not some, I think pretty good results on this, I'm not sure how useful will be Green's co-equivalences together with Green equivalence in this story. This is another question, very big question. Why so? Green equivalences are equivalences. From this point of view, they can be qualities. Then, quotient structure, L, R, H, they are without a partners relation. It is not inherited from original semigroup. Okay, let's go further. In order to solve or to make some kind of solving, we put a stronger condition. We put condition our background logic to be logic of constant domain. This is okay. Intermediate logic of constant domain is intermediate logic, stronger than intuitionistic, but still weaker of classical. And it is written, the proof theorem also still possess a strong constructive flavor. We, of course, important remark, as the subset and QD subset within CD logic coincide. So in what follows, we used notion of CD subset. So we, to the certain level, we follow the procedure which we have in solving Rie's construction. So we start for ideals, but this time, I think quite naturally, we start from principal ideals generated by an element. We prove that they are under this condition as the subsets, and even more that their ideals are co-ideals, one side or two side, depends on the starting principal ideal. Then we use those complements, these co-ideals to define the following relations. And then in continuation, we prove that those relations are in fact co-quasi-orders. So we call them Green's co-quasi-orders. We also got some connection in C. Green co-quasi-orders are a partners complement of classical Green's orders, and gives also some kind of connection between classical and this constructive case. Then, using Green's co-quasi-order, we define Gothic L relation in the following way. We defined R Gothic, J Gothic, H Gothic. Immediately from the theorem or proposition which was in the slide about co-quasi-orders. So the union of quasi-order and its symmetric relation is coequivalence. So it was shown that those type we have equality in this, which we used to define Green's relation D, got it D kind of, and then we got elementary relation between them. Of course, there are coequivalences, we call them Green's coequivalences. Then we also got some relation to classical Green relations. So Green's coequivalences are subsets of a partner's complement of appropriate, adequate classical Green relations. So what further? What is done further within constructive semigroup theory with the partners? An excellent result, an excellent paper. I recommend it for reading. If you think that classical inverse semigroup theory is difficult, please read this article just to compare things. So Cherubini and Trigeri in their paper, excellent paper. In fact, I communicate with Alexandra Cherubini. I invite her to be our also contributed talk, to give a contributed talk, but due to some circumstances, she wasn't able to join us. So I will only recommend this and go further, only to announce that we are also working within area on inverse semigroups. It is dedicated to co-congruencies, which separates the idempotence. This is a work in progress done by me and Romano. And I am very near to end this how to say, walk through achieved to the part of achieved results on theory and semigroup with the partners, possible applications, and just announced application in 1995 within computational linguistics, but in 1995 it is only announced. In 1995 there was not a theory developed. The theory we start actually to do that at the middle and the end of 2000s. So contrary to classical case, the application of constructive semigroup with the partners, due to their novelty, of course, constitute an unexplored area. In what follows, some possible connection between semigroups with the partners and computer science, oh, I didn't change. This is story for this slide, are sketched. One of direction of our further work is to be able to say more about these links. The study of basic constructive semigroup with the partners, as well as constructive algebra in general, as a whole, can impact the development of other areas of constructive mathematics. On the other hand, it can make both proof engineering and programming more flexible. And I'm really at the final slide of my talk. This citation, Professor Hounkonnou and me like very much. We took it as a motto of our series of conferences, Algebra Without Borders. So to paraphrase our colleague Frankel, taken from his book Love and Maths, Maths and Love, a lot of maths, a lot of love, we can say that algebra is much part of our cultural heritage as art, literature, and music. Algebra is like mathematics, also the source the whole mathematics. The source of timeless, profound knowledge, which goes to the heart of all matter and unites us across culture, continents, and centuries. This conference is also kind of proof of that. We have participants from 30 countries, from all continents. Thank you very much for your attention.
Well, thank you, Melanija, for your talk, which was quite comprehensive, if I may say. We will have, of course, discussion later about all of this according to the schedule. But now I would like to ask our colleague, Eric Darpo of the University of Nagoya to prepare, share the screen, and in a couple of minutes we will start just as the technical preparations are ready. Excellent. There we go. So, without further ado, let me announce Professor Eric Darpo from the Nagoya University, who is going to give his keynote talk entitled, as I understand from the slide, the contrastive kernel of a relation. So, Eric, please.
Thank you for the introduction, and thanks to the organizers for the invitation to speak here. So I'm going to speak on the topic of the co-transitive kernel of a relation, which is part of the work together with M.N.Hounkonnou, which you can read about in this preprint, which is on the archive with the new version of yesterday. Right, so I'm going to start more or less where Melanija started too, with the notion of apartness. So in classically, in classical mathematics, there is no kind of need for studying apartness relations separately. You have your equality and the complement, the negation of equality is, well, it is the apartness that you need. And these two concepts are completely dual. Not so in constructive mathematics. It is not always possible to prove even that the complement of equality is equality again. And the negation of equality may not have so nice properties, or we might not be able to prove so nice properties. And for this reason, when we are trying to do mathematics constructively, so constructively basically means in the way that we can implement and do stuff on the computer, it is often beneficial to have the notion of apartness as a separately, partly independently defined notion. The point of this is simply that you're able to do more things if you have apartness. In the classical case, you get the apartness for free. In constructive mathematics, you have to define it. You have to define it explicitly, but when you have it, you have more strength. You have more tools to prove things that you might not be able to prove. Also, many algebraic structures come equipped with a natural notion of apartness. So, for example, in the real numbers, so for the real numbers, we say that x and y, real numbers, are apart if and only if they are, well, I mean, the modulus of their difference is strictly positive. In other words, there is a positive distance between these two points on the line. And throughout, I will use this hash symbol to denote apartness relations. Another example is the set of binary sequences, where we say that two sequences X and Y are apart if there exists some index in which they are different. So one of them is 0 and the other one is 1. And I want to point out that in both these examples, the things that I have defined here, constructively equivalent, but classically equivalent, but constructively, these statements are stronger just than saying that X and Y cannot be equal. So just from the information that X and Y are not equal, it is not in general possible to deduce either this or this in the two respective cases. However, so while we have this structure given naturally in many algebraic structures, it's kind of stupid not to use them, right? And therefore it makes sense when we're doing constructive algebra, I think, and many people think, to look at algebraic structures which are equipped with apartness relations. So an apartness relation is any relation on your set which satisfy these three axioms. So first, it's got to be irreflexive. No element is apart from itself. Secondly, symmetric. And thirdly, we have this so-called cotransitivity, meaning that if two elements X and Y are apart, then any other element Z has to be apart from either from X or from Y. And this is an important axiom because it gives us a tool, it gives us a source of disjunctions, and disjunctions are otherwise in short supply in constructive mathematics. So it's the fact that we have such a thing gives us an important tool to prove stuff with. Right, so you might, so classically speaking, this is kind of completely dual to be an equivalence. So a relation is an apartness relation if and only if its complement, its negation, is an equivalence. So in particular, the negation of equality is an apartness relation, classically. And that's why we have no particular reason to think about them, specifically when we are doing mathematics in a classical framework. However, constructively, we can only prove one of these implications, namely that if you have an apartment, its negation is an equivalence, but not the other way around. All right, and perhaps about notation here, I should say, well, when I'm speaking about a relation, I always think of this on a set X. Say, I always think of this relation as a subset of X Cartesian product with itself. So when I'm writing this negation symbol, well, that is a complement. That's everything that is not in that subset. Right, so we start with our algebraic structures with apartness, and then because we're doing algebra, typically we will want to construct factor structures. And here one problem occurs, namely, which Melanija already mentioned, that in general, if you have some factor structure, congruence with respect to a congruence on a semigroup, or with respect to any equivalence on a set, or with respect to whatever is the appropriate notion in the type of algebra that you're doing, there is no way, in general, there is no canonical natural way of defining an apartment relation of the factor structure. So the idea here, so one idea is to start with, instead of starting with a congruence, you start with a co-congruence. Then you have seen in the slide about Reed congruence from the previous talk that you can get an apartness relation on the factor structure. Here I'm going to look at a slightly different approach, namely, so just, you might even forget about the relation you had in the beginning. You just look at this set and you try to find the maximal possible apartness relation on it. So the maximal possible apartness relation on this structure would be the maximal co-transitive subrelation of this negative row. So, so it's being a subrelation of negative row. This is necessary for irreflexivity, right? And this, okay, right. And if you are dealing with an algebraic structure, as for example a semigroup, if you want your apartness to be compatible with the semigroup structure, you will need some kind of compatibility condition for that. This is a technical issue. It can be solved with some effort, but I will not delve into that in this talk. But I will, so for this, the purpose of this talk, let's, for simplicity, just work with set and an equivalence. So to find, okay, so I wanted to construct the maximal co-transitive subrelation of a given relation. So in the classical case, when we are dealing with equivalences and congruences rather than with co-equivalences and co-congruences, we have a similar construction, right? We have the transitive closure, which we all know about. You know that an element, we know that a relation is transitive if and only if its composition with itself is contained in alpha. And starting with any relation alpha, we can construct its transitive closure in this way, right? This is classical and well-known stuff. Now, since we are trying to do something analogous or something dual, so we will try to in some way compare this. So I'm now looking for the maximal co-transitive relation which is contained in a given relation. So this in some way is a dual construction. So instead of composition of relations, I will need a corresponding notion, which was first studied by Romano and called it the field product. It is denoted like this, and it consists of all the pairs x and y, such that for any z, we have z related to x, or x related to z, or z related to y. And then it's easy to see that the relation alpha is co-transitive if and only if it is contained in, well, it's in alpha field product with alpha. Okay, so to continue this analogy here, I should probably write some co-transitive kernel here as being an intersection over one positive n of well, field products of alpha with itself. This, however, has some problems. The first problem, which is again is already, I think, was already mentioned, is that the field product in general is not associative, or it cannot be proved constructively to be associative. So this means that the nth product of alpha with itself is not well defined, right? Because it depends on how you distribute the brackets. This is not the big problem. So what we do instead is we check the set of all products, all field products that can be formed from alpha, just iteratively. Alpha product alpha is alpha product alpha. Well, I mean, you just close alpha. You generate all field products you can, starting just from alpha. And then my corresponding notion, so my candidate for a co-transitive kernel would be this, which I denote by alpha tilde, which will be the intersection of all such products. So all pairs which are in every possible field product. It is easy to see, or it is reasonably straightforward to see that if I have a cotransitive relation which is contained in alpha, then it will be contained in this one. So if this one is cotransitive, then it is the maximal cotransitive relation contained in alpha. But is this incotransitive? If you're arguing within classical logic, it's completely obvious that it is. But now we are dealing with this constructively, and we have to be more careful. So I'm going to give you an example. So let's look again at the set of binary sequences, call it X. And I say define the relation alpha by saying that alpha and that two binary sequences X and Y are related to each other if and only if there exist two indices in which they are different. So they differ in at least two places. And then with some effort, you can show that this alpha tilde relation then means to differ in infinitely many points. So for any index n, there exists a bigger index m such that X and Y are different from each other. And next, you can show that you can't show that this is cotransitive. So alpha tilde is being cotransitive. If you assume that alpha tilde is cotransitive, then you can show this principle called the limited principle of omniscience. So that principle says that for any binary sequence, either it is constantly 0 or there exists an entry in this infinite sequence which is 1. And this, while true classically, cannot be proved constructively. So you cannot prove constructively that alpha tilde is cotransitive. And actually the converse holds as well. If we assume that the limited principle of omniscience holds, then we can show that alpha tilde is cotransitive. And actually, we can show that if we assume LPO, we can actually show that alpha tilde is cotransitive for any relation alpha. However, this is not a constructive principle, so we can't get there. We have to. We are not possible constructively to prove that this thing is cotransitive. So my answer to the question is no, not in general. However, this doesn't mean that we never can prove that alpha tilde is cotransitive. For some classes of relations, we can. And I'm going to present to you one such class. Namely relations on finitely enumerable subsets. So by definition, a set by finitely enumerable sets. So by definition, a set is finitely enumerable if it is a factor set of a finite set, or equivalently, if there exists a surjective function from the set of integers from 1 up to some number d on 2x. So this means that there is at most d elements in x, but maybe some of them are actually identified with each other, and we might not be able to tell exactly how many elements x has. So this is a weaker assumption than being finite. It's a larger class constructively. Then, if you have a relation alpha on a finitely enumerable set, then alpha tilde is cotransitive. And in this case, this alpha tilde, I will denote it by C of alpha, and I will call it the cotransitive kernel of alpha. So it is the maximal cotransitive relation contained in alpha. So as a consequence of this, we can say some things about finitely enumerable sets and about the partners on finitely enumerable sets in particular. So, For example, whenever you have a finite, okay, so from now on, X is a finitely enumerable set. And the first thing I can say is that there exists a unique maximal apartness relation on this set. Right? And that apartness relation is simply the cotransitive kernel of the negation of the equality. So this, if I have any other apartness relation on X, that apartness relation will be contained in this one. So this is the best we can do in terms of apartness. And if I just translate this into factor structures, I get a unique maximal apartness relation on a factor structure X over rho, simply by taking the cotransitive kernel of the complement of the congruent row. So this works on finitely enumerable subsets. This is the first consequence of our result. Second is the one which you have already seen on Melanija's slide. So in general, right, we have equality, which is an apartness. We have equality, which is an equivalence relation. We have apartness, which is some kind of co-equivalence, we call it. So some kind of dual structure. And as we said, the negation of apartness is an equivalence relation, but we cannot prove in general that every equivalence relation is the negation of an apartness relation. So you might ask, it's a natural question to ask, which equivalences arise as the negation of apartness relations, of co-equivalences. And we can answer this question. So here, think of alpha as being an equivalence relation, but I don't need the symmetry. So I just assume that it is reflexive and transitive. Then the following statements are equivalent. First is that alpha can be written as the negation, as a complement of some cotransitive relation. And the second is that alpha is stable. In other words, that the complement of alpha again is alpha. So some relations satisfy this, others simply don't, or we cannot prove that they satisfy this, at least. Okay, so again, this works on finitely enumerable sets. And in particular, I have my finitely enumerable subset has a tight apartness relation. I can define a tight apartness relation on this set if and only if the equality relation is stable. So tight means that the negation of the apartness is the equality, right? I'd like to say just a few words or give an outline of the proof of this. So first, look at the statement A here. So if alpha can be written as the negation of some cotransitive relation, then it can be written as the negation of the largest one contained in negative alpha. So A is equivalent to saying that alpha is the complement of the cotransitive kernel of the complement of alpha. This in turn can be translated into saying that whenever I have a beta in this thing of negative alpha, then the negation of that beta is again alpha. This implies that alpha is stable. This is kind of almost immediate. However, it is the implication from B to A which is difficult. Okay, so now we shall prove then. To prove the strategy of the proof here is that if I have a beta in this set, I want to prove that the negation of that is the double negation of alpha. And then A will hold if and only if the double negation of alpha is alpha itself. So one implication we get for free. So since beta is here, it follows by definition that beta, more or less by definition, that beta is contained in the negative of alpha. And if I just negate this inclusion, I get that the double negation of alpha is included in the negation of beta. So that gives me one implication. So it remains to prove the other inclusion, that negation of beta is included in double negation of alpha. Or equivalently, this is the same thing as saying that the negation of beta intersected with negation of alpha is empty. This is what it means. Excuse me. Oh, what shall I do now? I need to. Right. Yes, there we go. So, how do I prove that? I want to prove that. Okay, I'll write this here. So to do this, I will assume I'm going to prove a negation. I assume that there actually exists an element in this intersection, and then I will prove a contradiction. And that means that the intersection is empty. Even in constructive logic, this is how it works. So assume that this is inhabited. And then right, and then I will make another assumption. You will see where I'm going with that. So I will assume that alpha, which I remind you we view as a subset of x cross x, is detachable. So detachable means by definition that for any element in this set, I can decide if it is in alpha or if it is not in alpha. In other words, for all x and y in X, I have either X related to Y by alpha or not X related to Y. And now you will recall that X is finitely numerable, and I will call the elements of X, I will call them X1 up to XD. Although these elements might not be distinct, or might not even be able to tell whether they are distinct. But at least there are no other elements than these ones. So then I can just reformulate this statement as a conjunction to get rid of the quantifier. So write I and j going from 1 up to d. And then I write xi alpha xj or not xi alpha xj. Right? This is equivalent. And perhaps I will call this. I will call this statement P alpha. So notice here, this will be important in a while, that this is a quantifier-free statement. And it is a quantifier-free statement, and classically this is tautological, right? For any any statement at all, you have either it's true or it is false. So classically, this is tautological. And then maybe I'll write the punchline here directly. We have a result called Glivenko's theorem, which tells that if you have a quantifier-free statement, which is classically true, then its double negation is constructively true. So Glivenko's theorem tells you that the double negation of the statement is true constructively. Okay, I have assumed that alpha is detachable. I have assumed that this is inhabited. Okay, however, it is easy to show that if alpha is detachable, so every pair of elements is either in or out, right? So in that case, it is easy to prove that the negation of alpha is co-transitive. Because essentially now since we have assumed that alpha is detachable, essentially we are working in a classical situation. So it is co-transitive. However, so co-transitive, what does this mean? This means by one of the basic properties that I gave you in the beginning, that negative alpha is contained in the field product of negative alpha with itself. And then by an induction, so you get that negative alpha is contained in negative beta. Remember here that, sorry, not in negative beta, but in beta. So remember here that beta is any element that can be formed by taking field product of negative alphas. So I have this statement, but that, of course, implies that the intersection of negative alpha with negative beta doesn't contain any elements, right? But hey, we have assumed that this intersection does contain elements. So we have reached a contradiction, which I denote by this bottom symbol. So what does this prove? Well, this proves that the assumption of detachability gives a contradiction. So from this part here, I conclude that alpha is not detachable. In other words, the negative, so this is a statement that alpha is detachable, and I have proved that it's not. So I have proved that not P alpha holds. But then we have Glivenko's theorem. Glivenko's theorem tells us that constructively, the double negation of P alpha is true as well. So I have that negative negation P alpha holds, and I have that negation P alpha holds, and I have that negation P alpha is impossible. So this again implies, well, an absurd state. This is an absurd statement. It implies a contradiction. So what we have done is we started with assuming that this intersection is inhabited, and we proved a contradiction. So the conclusion of that is that this statement is impossible. In other words, that this intersection is empty. And that is what we needed to That is what we needed to conclude the proof of the theorem. So I have used my 35 minutes at least. So I will stop here and thank you for your attention.
Thank you, Eric.
As a consequence, all the results we prove are valid both in classical mathematics and in other varieties of constructive mathematics. I'm going to illustrate several features of constructive mathematics, classical equivalent notions, which are constructively inequivalent, the use of Brouwerian examples to show that a certain statement is non-constructive, the use of cotransitivity, and so on. First, some preliminaries. We will only deal with sets of apartness. Thus, each set will be endowed with an equality relation, but also with an apartness. You know what is an apartness and irreflexive, symmetric, and cotransitive relation. The apartness is tight whenever, if two elements are equal, whenever they are not apart. As an example, we have the standard tight apartness on the real number set. Two numbers are apart whenever we can insert a rational number between 0 and the modulus of x minus y. This is the constructive meaning of positivity of real numbers. And of course, we can extend this apartness to an arbitrary metric space. Two elements are apart whenever the distance is positive, strictly positive. When we leave the metric spaces, it is more difficult to work with the apartness because we lose the numerical meaning. So constructive algebra is difficult indeed, because in analysis we usually work with a metric on the space we consider. Anyway, we have usually we have two complements which are not equivalent: the logical complement of A and the apartness complement. We work with binary relations, so we need the apartness on the Cartesian product, which is defined here. Either the element on the first position are apart, or else this pair of elements. When dealing with order or quasi-order constructively, we have a major problem in comparing two elements. Even for real numbers, we cannot decide for any two numbers whether they are equal or apart. Equivalently, the trichotomy law doesn't hold constructively. Actually, these statements are equivalent to the so-called limited principle of omniscience, LPO, which is a major source of non-constructivism. Even weaker statements are non-constructive because they lead to non-constructive principles such as the weak limited principle of omniscience or the lesser limited principle of omniscience. So we have to be careful to avoid these non-constructive statements. However, for the linear order relation greater than, the cotransitivity holds. So we have a suitable substitute for the trichotomy law. Thus, by starting with a relation greater than, we then defines a relation less or equal to by negation. So the idea is to extend a similar construction for dealing with order or partial order. So a reasonable approach would be to consider a cotransitive relation whose logical complement is a partial order, respectively only a quasi-order. This was done by von Plato for defining partial order constructively, and by Romano, Mitrović, and others for quasi-order. In conclusion, co-quasi-order is a strongly reflexive and cotransitive relation. And when we replace strong irreflexivity by irreflexivity, here is strong irreflexivity, and we replace by irreflexivity, and we obtain the definition of a weak co-quasi-order. Since strong irreflexivity entails irreflexivity, clearly every co-quasi-order is a weak co-quasi-order. And moreover, the logical complement of any irreflexive relation is reflexive, and the logical complement of a cotransitive relation is always transitive. So the logical complement of a weak co-quasi-order is necessarily a quasi-order. So from now on, a quasi-order will be obtained, will be considered only as a logical complement of a given weak co-quasi-order. Of course, the previous talk shows us that in certain hypotheses we can do in the converse way, but only with strong hypotheses of the set should be finitely enumerable, if I understood correctly. Following from Plato, we say that X exceeds Y when we talk about the weak co-quasi-order, and of course X doesn't exceed Y when we talk about the quasi-order. For non-tight apartness, we can construct a counterexample of weak co-quasi-order, which is not a co-quasi-order. However, this is not very surprising because when we deal with apartness, with an apartness which is not tight, we could obtain all sorts of pathological situations, and usually they are also classically valid. The classical proofs are constructively valid in these cases. So, in my opinion, it would be better to pay attention to the tight apartness case. Here, both relations are classically equivalent, so each one can be viewed as a constructive counterpart of a quasi-order. Melanija used the term constructive friend. It's more metaphorical, yeah. Contrary to the non-tight case, it is impossible to obtain a counterexample here, but we can prove Brauerian example. We can find a Brauerian example to show that 2 implies 1 entails the Markov principle, which is not accepted in Bishop's constructive mathematics. It is accepted in the constructive mathematics developed by Markov and the Russian school of constructivism, but not in Bishop-style mathematics. To give that counterexample, let's consider an arbitrary real-valued function and define x exceeds y if and only if f of x is greater than f of y. We obtain a weak co-quasi-order, which is a co-quasi-order if and only if f is strongly extensional. So if every weak co-quasi-order were a co-quasi-order, then every real valued function would be strongly extensional, and this statement implies in turn the Markov principle. So we cannot accept the equivalence between 1 and 2. A few more words about co-quasi-order and the relationship between the two variants of co-quasi-order. We will present again as Eric Darp discussed about QD subsets and also Melania Mitrović. A subset A is QD, a QD subset, quasi-detachable, if it satisfies this condition, which of course in classical mathematics, when the apartness is the negation of the equality, is vacuously true. We have nothing to prove. But constructively, the situation is completely different. If we accept that every subset is a QD subset, then LPO would hold, which of course it's not the case. One can prove that each co-quasi-order is both quasi-detachable and it satisfies this condition. The two complements coincide. This was proved, for example, in a paper by Mitrović, Silvestrov, Hrvenković, and Romano in 2019, I think, and maybe earlier. Conversely, we can find a nice result. Each weak co-quasi-order satisfying one of these properties is necessarily a co-quasi-order. So you obtain 3 equivalent conditions for a co-quasi-order. Of course, if we deal with a weak co-quasi-order, we get a condition of detachability similar to this one, but of course weaker. And it's not very interesting. Now it's time to examine positive quasi-orders. From now on, we'll consider a weak co-quasi-order on a semigroup with a partness, and the corresponding quasi-order given by the logical complement. For a binary relation rho on S and an element A of S, we denote as usual A rho and rho A. And now I'll try to give you several definitions of positivity. In the last years, the constructive positivity of quasi-order relations has been investigated in several papers published by Mitrović, Romano, and others. we'll discuss here the more general case, the weak co-quasi-order. As it usually happens in constructive mathematics, we can define several counterparts of a classical notion. First, we will say that a weak co-quasi-order is weakly positive, WP, if it satisfies the classical condition of positivity. In other words, its corresponding quasi-order should be positive, according to the classical definition. So probably here is not very interesting, but we have 4 other definitions: positivity, strong positivity, SP, CP, SCP. C comes from complement. We define here positivity using the partner's complement. This approach was done for co-quasi-orders in a paper published by Hrvenković, Mitrović, and Romano in 2016. For a tight partners, the 5 conditions are classically equivalent. What happens in the constructive setting? First of all, we have a chain of implications. So from bottom to top, each condition implies the next one. For the implication SCP implies CP, we only need to replace X here by A in the definition of SCP, and we obtain CP. So the other implications are easily to be proved, so I'm not going to give you details unless you want to ask me something. And now let's see what happens with the weakest variant of positivity. As in the classical case, we can obtain several equivalent conditions. And more or less, the classical proofs are valid. So it's not very interesting to discuss these equivalences. Moreover, we can find 4 other equivalent conditions by using the logical complement of the quasi-order. That is the relation obtained from the weak co-quasi-order by applying the logical complement twice. If the apartness is tight, we might consider an apparently weaker condition, which actually is equivalent to the previous one. And this is a nice example of application of the proof by contradiction, because in the classical case, basically we have nothing to prove. We can consider 2 cases when either in the classical case, either A equals AB, or else A is apart from AB. However, in the constructive setting, we cannot split the proof in these 2 cases because this splitting entails LPO. So we'll give an alternative proof we have to prove that A doesn't exceed AB. So we will assume that A exceeds AB, and we hope to derive a contradiction. If we make this supposition, then A equals AB. Indeed, otherwise, according to WP1, A doesn't exceed AB, which is contradictory to our supposition. So we have A equals AB, but in this case, according to the reflexivity of the quasi-order, we obtain again a contradiction. We also have several equivalent conditions for positivity. The proofs are quite easy, and I'm not going to bother you with details. And as in the case of weak positivity, we can obtain an additional condition for the tight apartness case. The proof is similar. Somewhat surprisingly, P and WP are equivalent. And even more unexpectedly, the proof is straightforward. Usually the constructive counterparts, also classically equivalent with classical notions, are constructively stronger, but not in this case. So it's somewhat surprisingly. Furthermore, if you consider a co-quasi-order, so the relation should be strongly reflexive this time. All the positivity conditions are equivalent. Again, this is somewhat surprisingly. Here, we don't need the tight apartness. The result holds in general. To prove this, we only need to prove this implication. The weakest positivity implies the strongest one. And to do this, we only apply the definitions, so it's not a very complicated proof. Now I'm almost finished, so maybe it would be interesting to see what happens in particular conditions. For example, if we consider a monoid, we can obtain, as in the classical case, that the identity element doesn't exceed any element. But more interesting, we obtain that each strongly positive weak co-quasi-order is actually a co-quasi-order. So here the two notions coincide, but you have to be careful only if we have at least strong positivity. So probably we have a borderline between the weaker positivity, WP, which is equivalent to P, and the stronger variance, SP, CP, and SCP. Now it's time to discuss a little about possible further work. As a particular situation, for example, it would be interesting to analyze the linear case. A linear weak co-quasi-order is nothing else than an asymmetric weak co-quasi-order. That is a preference relation. The preference relations have been examined in constructive mathematics by mainly by Douglas Bridges, and there are important theorems of representation. The idea in microeconomic theory is to represent a preference relation by a utility function. So maybe it's interesting to analyze this type of relation according to our approach. So from an algebraic point of view, we could try to find other particular situations where strong positivity is sufficient for obtaining a quasi-order. And of course, we have an important open problem, I think, to clarify the situation between the weaker positivity and the stronger variant. Do we have a borderline in between, or they are equivalent even for a weak quasi-order? My feeling is they are not the same, so they are not equivalent, but I don't have any clue for a proof. So we need a Brauerian example to prove this. The last problem and that's all. Should we work with weak co-quasi-order or with co-quasi-order? Well, the answer, I think the answer is more complex than yes or no. If we want to advance in the algebraic theory, clearly we need the stronger variant of quasi-order. So we need the stronger reflexivity in order to get substantial results. However, now and then maybe it's reasonable to stop and see what happens in the weaker case, because we might reveal distinctions which could be hidden here in the stronger case. Thank you very much.
Okay, we are then finished with the talks in this morning's session, a little bit earlier than planned, as far as I can see.
Mm-hmm.
Okay, so Melanija, what do you say? Do we start immediately with the discussion, or?
Yeah, immediately.
Okay. Okay, so yes, first of all, I would like to thank all the speakers of this morning's session and offer an applause. And so, please, hereby I open the discussion concerning these 3 lectures.
Okay, I have a general consideration, then I have a couple of questions. Okay, the first one is when I met Melanija a couple of years ago, and she sort of, you know, explained me what this constructive things is all about. I started wondering, I mean, if this is a new way of looking at mathematics, right? It stands to reason that in fact it should proceed in a similar way. In what sense? What I see here, I see some very ground, you know, concepts and ground considerations. For instance, all the stuff that is done on relations on sets. And then I see some specific instance, some specific algebras like semigroups or even groups and rings and whatever, and inverse semigroups. And now I do believe that we should try to see this stuff as applied to general algebras. So sets with operations without not caring too much about the nature of the operations. Of course, I mean, if you look at orders, but then again, you can have orders without operations. I mean, you just look at posets. You don't need a semigroup operation. So what I did, I tried to see how these concepts can be stated in a very general way. And I believe I made a draft to Melanija, right? Did you get
Right.
I mean, just very simple stuff. I mean, just the basic concepts. How can you frame them in the context of general algebra?
And I promise that I will go deeply in that after conference.
No, I mean, that's just what, you know, because in my opinion, but of course, I mean, I'm biased, right? Because that's what I do. So in my opinion, the approach, I mean, the general algebraic approach should be a little bit more interesting because, I mean, we are really dealing with a new way at looking at algebraic structures. In particular, we are studying properties of algebraic structures that does not come out if you use classical logic because they get identified, right? They collapse in classical logic. So the point is that, you know, what can you say about general structures without, you know, saying too much about the nature of the operations involved? You know, using classical logic, you can say a lot. Using intuitionistic logic, you can say probably much less from a certain point of view. So since you have certain obvious limitations, I mean, you cannot have all the nice and useful relations that we normally have in algebras, like, for instance, infinite direct products, for which you need the axiom of choice. But it might shed some more light on the general nature of the question. And this is my general consideration. Sorry if I bothered you with this, but I mean, you know, I felt like I had to say that. Then I have a question for Eric. Now, and this is a silly question, so forgive me in advance. Okay.
You give a silly answer.
Oh, okay, fine. I'll settle for that. Now, you define a set to be finitely indexed, if I recall correctly. If it's the homomorphic image of a finite set, right? Basically.
No.
I mean,
I defined, so the definition is that if I have it, that is, well, I mean, you can define it, you can, so by a finite set, we usually mean something which is in bijection with
yes, okay,
some set of positive integers. That's a finite set. And that finite sets behave like completely classically.
Yeah, sure.
And we have finitely enumerable, then you are a factor set of such a set. So there is a surjective function from a finite set onto your finitely enumerable
Can you
set.
give an example of a finitely indexed set which is not constructively provable to be equivalent to be finite?
Well, yeah. Then perhaps I shall share my screen again.
You can take a set of solutions of a quadratic equation, for example.
Okay.
Real numbers. We have at most 2 real solutions, but we cannot decide constructively whether each equation has either 2 solutions or 1 solution or none. So this implies the limited principle of omniscience.
Okay. Now I get it. Now I see where the LPO comes in, because I mean, of course, I mean, you have to look at triples of coefficients, and then you have to be able to exclude some of them. So clearly you need something of the kind. Thank you very much. Now it's way clearer. Okay.
Right. I mean, another another example would be like, okay, so let X be set of 0 and 1, and then we just define an equivalence relation on these two, saying that, okay, so let P be, for example, the proposition that Goldbach's conjecture is true.
Okay.
And then you say that, yeah, 1 is equivalent, 0 and 1 are equivalent.
Okay.
if Goldbach's conjecture is true, or if Goldbach's conjecture is false. Until you have proved or disproved Goldbach's conjecture, you cannot tell whether or not 1 and 0 are different. But you can, of course, you can, right, okay, so on this set, right? But of course you have a surjective function from X.
Yeah. I see what you mean. You cannot tell if 0 and 1 are related until you solve that problem. So I mean,
well, it's impossible that they're not related, right?
Yeah, sure. That's the usual. Yeah. Okay. Now it's
for Goldbach's conjecture, substitute just any proposition.
Yeah.
So the statement. So if every finitely enumerable set is finite, that means that for every proposition I can decide P or not P. But if I can do that, then I'm not doing constructive logics any longer. I'm doing classical logic.
Okay. Thank you very much.
Okay, maybe I have a question back about the general consideration. So what you are suggesting is to try to do universal algebra or something similar.
Constructive.
Yeah, I thought about it. Well, I didn't think very deeply about it, but for example, the isomorphism theorems are still valid. And
that's what I was trying to do. I was trying basically to do the same, to prove the generic homomorphism theorem. And the problem, of course, is with the third homomorphism theorem that is very hard to understand in a constructive sense.
Okay. I'm not sure. I imagine that it would be possible to kind of make it work. With the
sure. I mean, you can make it work, but the problem is how you can make it work and why the way you make it work makes sense. that's
Okay. I saw the history of all this is so rich, and I'm really fascinated by the so many open questions in front of us. And I would like maybe to ask Melanija to share with us more about the different steps of this theory development. For example, talking more about the history of Green's relations.
Okay, thank you. But let me remark first, even this conference, even this event, even this day is kind of history for the theory of semigroup in the partners, because we started to present our results hardly, and we fight for this for years. But then 9 years ago, I think Igor also was a witness of both historical facts. He knows what I'm going to talk about. Then the first talk ever given on any semigroup conference about this point of view on semigroup theory was done in Uppsala, a conference in Uppsala on 2nd of September. So it is kind of anniversary. And since then, that I gave a lot of lectures on conferences as invited speaker, and it was how to say, it was silence after my talks. Now we have a section and we have a discussion. So yes, this is a history. Also, section on a conference dedicated to semigroups and discussion. Talking about the Green's equivalences, to come back, what motivates us to do that? Of course, I partly answered during my talk. Green equivalencies are main tools in dealing with classical semigroup theory. Of course, one of the questions we posed early, you can find this question in our papers from 2013 and 2014. We posed this question. We remarked that this is not so easy to find kind of friends of green relations within semigroup theory. We developed. So Eric was in niche. The history of the solution begins in the end of 2015, 2016, when Eric was here. When Eric was a guest, 3 months guest due to Erasmus Plus project of our center, and when I presented to him our problem. The problem was the following. Yes, in 2013 we managed to discover isomorphism theorems. We solved this problem for set for apartness. It is the first time to have such kind of solution. And then the procedure was the following. It is a procedure which are somehow copied from group theory with tight apartness and ring theory with tight apartness. In group theory, the quotient structure problem is solved that it is the starting point is co-normal group, and then the problem is set. In rings with tight apartness, the starting point was co-ideal or anti-ideal, it depends. And then the complement is ideal, and then we were able to have a partners relation on a quotient ring or in previous case group. So yes, the direction from group theory and ring theory was start first with constructive notion. And we did it. We use some earlier Romano works. We start with co-equivalence. We got result. We got that two complements coincide, and then everything was the existing properties of co-equivalence guarantee that we will obtain a partners relation on the quotient structure. That was the procedure for solving quotient structure problem. But we have green equivalences which are equivalences. The theory of equivalences work in constructive setting without any problem, more or less similar. So, but we don't have again quotient structure on factor semigroups induced by those equivalents. So naturally question which arise here, and Eric and I spent a lot of time discussing about that. I hope Eric still remember those days, was what if we start from equivalence? What if we start from equivalence? And whether, the first question, of course, very naive, was whether equivalence is kind of complement for certain constructive defined relation, co-equivalence, co-quasi, whatever. Then we make example. Actually, Eric made example that he found equivalence with the complement which is not coequivalence. And then together with Baroni, we remember, or we got to the point that this is the main problem is in co-transitivity. Co-transitivity is not guaranteed in a vice versa direction. So we cannot prove constructively that any transitive relation has a complement which is a co-transitive. And this was beginning of the story. It was a very interesting problem. Very interesting problem, a difficult problem, problem which was solved with Eric. I'm sorry that Eric present only a part of the results, but of course there wasn't time to present the whole story. There is more about that. The results can be found in an archive paper Eric mentioned. So that is how we got to this, to co-transitive kernel, to a whole story, and then in continuation we finally reach Green's relation. What is the big problem from my point of view? At least me, I'm not still sure about general methods for handling with this approach, with these semigroups. Okay, even in classical semigroups, there are not unique methods to approach them and to study them. But there are mentioned several, few of them, 3, 4, 5, never mind, which are considered to be among general. I still cannot say, maybe I have some kind of feeling, but I still can't say which direction, which leads us to kind of method which can be considered something like general, belong to general. Yeah, I have to say that I was pretty much like, sometimes I feel myself like, how to say, the boy from network cartoons who was ordinary boy, and in one moment he ate banana and then he became suddenly a banana man. I don't know whether you have opportunity to see that cartoon. So the similar story goes with me. In one moment I was working within the classical semigroup theory. In another, what kind of banana I eat, I can't tell you. I woke up like working in constructive theory, constructive semigroup theory. But anyway, I found it very, very interesting, very challenging. Open problems. Oh, when we started to work, there was nothing. It was empty space. We started to work without clear notion and notation. We may, even if you go through our papers, you can see that we changed several times our notation and notions, and it was not so easy when you are starting to build new town on an empty space. But okay, this discussion, there are open problems. Open problems, besides of finding, personally, I'm interested to find something which will be some kind of constructive friend, that I'm using to say, of semi-lattice decomposition, being a semi-lattice decomposition within classical semigroup theory. I'm interested in how this will work, and some initial steps towards that are done. I have to remember that still we didn't up to now, we didn't tackle regular semigroups and their investigation from constructive, a lot of. But what maybe to end, what is very important from inverse semigroup theory point of view, you know, there is abstract definition of inverse constructive semigroup, inverse constructive semigroup with the partners. And there, Frigeri and Cherubini give an excellent, how to say, they connect these with a certain type of partial transformation which are done within subset which are QD subset within CD logic, yes. But what is interesting, not every inverse semigroup with the partners arise in this way. They also gave a Wagner-Preston theorem for this case, but also the conditions are stronger in the sense of some assumption about type of relation between equality and a partners are already relation on idempotence, but anyway relation. So coming back to finally to Paolo and his comment, yes, I think that it is also one of direction which should we start to develop. Yes, Paolo already have done something. Yes, he sent it to me some time ago, and we will probably make some breakout conferences. We organized, Norbert and me and people, some other colleagues, 3 big conferences in the last 5 months. So I talked too much.
Thank you very much. But I have a question to everyone. Is it any reference to quantization of semigroups?
Of?
Quantization of semigroup.
Quantum. What does it mean?
Quantization, you say?
Of?
Quantization
of semigroup. Do you know any reference to that?
In which sense?
In the sense of quantification.
Quantification.
Yeah.
Quantification.
You mean some Q analogs?
Hmm? No. We didn't we didn't consider something.
No. Do you know any reference to this aspect of the question?
Quantization in what? About quantificator, their use? I don't understand the question.
Okay. Do you mean like Q deformations? Like
yeah, deformation.
Directions.
Okay. No.
I have no idea if that has been studied classically at all.
Okay.
No. The answer is no, we didn't. We don't up to now.
No, if anyone in the anyone related to semigroups tackle with such problems, that is.
But I think that I found a kind of paper.
Mm-hmm.
And I can't remember exactly. It was it was several months ago, about kind of application, I think, if I'm not wrong, in mechanics or special area of physics. And it was written by actually very known constructive is Malvey, right, Marian? Malvey, I found something written by him.
Maybe
But,
maybe with those who apply semigroups to solve differential equations.
But what is the
In
problem?
analysis, in functional analysis, maybe, I don't know.
But what is the problem? The theory is quite new. The theory is in his development. So I think that there is
aspect is developing, but the classical one is quite.
I'm talking only about constructive point of view. If we are going to talk about classical and their application, then my answer will be quite different.
Okay.
Because there are books on that, there are a lot of papers on that, on applications in different branches of physics, in engineering, in thermodynamics, then the answer is quite different. But when constructive semigroup with the partners are in question, then no, because the theory is new. We are on our way to popularize it, and I assume that it took the time. For example, what is also one of the problems I posted in my presentation, it is that we were motivated to develop this theory. One of main motivation came from artificial intelligence. We took the definition from automated reasoning area from the project done by an imaging group in beginning of 2000, and the project was about the formalization of fundamental theorem of algebra on proof-assisted coq with intuitionistic background. In order to be able to do that, they created algebraic hierarchy. And of course, semigroup do appear, but do appear definitions. Definition is semigroup with tighter partners and commutative. So that motivate us to proceed. Now we have results that semigroup, I mentioned also this, semigroup with partners and equality independent also prove that should be considered within this scope. And I used to compare that from my place, I crossed the river. We crossed the river with one tiny unstable bridge. I took something in the town, buy something in the town, which is called artificial intelligence. I turned back to my place. In meantime, bridge collapsed. There is no bridge for me, for us now to come back to this area. And this is one of big problems, and it's something very, it will be a very big achievement if we manage to build such a bridge to be able to return.
Yeah, I think there is one positive point. It is the existence of the associativity properties, which is the starting point of all theory of deformation. So this could be also some perspectives to be developed.
And of course, if you are going about future work, non-associative algebraic structure with the partners are also in interest.
Yeah, but the already existing associativity properties is a very good point for the development of such a kind of deformation of the, because it is essential for all theory of deformation. Okay, thank you for your clarification. Chair, I finish with my question and suggestion. Chair.
Igor.
Okay, are there any further questions maybe, or we can slowly conclude this discussion? If that is the case, and it seems to be the case, then I will thank all the speakers once again, as well all the participants in the discussion. And this brings this morning session to a close. In the afternoon, we will have a special colloquium of application of semigroups within sciences. Thank you very much.
Thank you very much. You're welcome. Good afternoon, everyone. Let's start now with the last colloquium of this conference, colloquium on applications of semigroups within sciences. It will be shared by Ryszard Rudnicki. Ryszard Rudnicki is a professor at the Institute of Mathematics, Polish Academy of Science. He's graduated from the Faculty of Mathematics, Physics and Chemistry at the University of Silesia, Katowice, Poland in 1980 for his MA and PhD in 1984. He has written more than 90 mathematical articles and 3 monographs. He is interested in biomathematics, population dynamics, physiology, genetics, theory of semigroups of operators, partial differential equations, chaotic and ergodic properties of dynamical systems, and stochastic models. He was the organizer of 8th European Conference on Mathematical and Theoretical Biology, Krakow, in 2011. With almost 1,000 participants. He was the member of the board of ESMTB from 2011 to 2019. Please, Professor Rudnicki, take the floor.
Thank you, Norbert, for introduction. I would like to share screen, first of all, with my talk. I hope. Yes. Okay. I will be talking about something different than the main subject of this conference, but I think that it could be interesting to have some taste of some different aspect of semigroup theory. Well, first of all, I would like to say a little bit about me, but I would like to, before sharing the screen, I would like to show you something. Well, how to stop sharing, yeah. I would like to show you the map of Poland. You see probably on my t-shirt, there is a map of Poland, yeah, like that. Here is the capital of Poland, is Warsaw. And I am from Katowice, it's in the southern part of Poland, like here. So it's something similar like in Niš. Niš is also in southern part of Serbia, and Belgrade is something here.
Yeah.
So it's very similar. Okay, so I share the screen, I hope, moment. Well, as you see, the title of the subject is Asymptotic Decomposition of Stochastic Semigroups. Well, I will explain the subject after a moment, but something, how to, well, how to do it with this. Which one? A moment. Page maybe page 1. Okay, there is a picture from Katowice. It's a place where I used to live. And you see a very interesting place at this city. Katowice is the capital of a very industrial place in Poland called Upper Silesia. I hope that it will be better to not use microphone, such things. And now we are in Niš. There is a University of Niš here, the main building. So we change the place. How to do it? Which one? No. I would like to change page by page. It's very strange because it works before. No. Sorry for a moment. So I should do it in this way. Okay, there is some outline of my talk. So first of all, I will say what is a stochastic semigroup and some result concerning asymptotic decomposition of such a stochastic semigroups, and then give some application of such subject. Okay, and I must say that semigroups are like dogs. There are incredibly many of dogs and semigroups, and usually people do not know if you're doing something in semigroups, the subject can be completely different. And in some sense, my subject is not strictly algebraic, but it is connected with some stochastic processes in some sense. But the name of stochastic semigroups doesn't mean that these semigroups are stochastic. These are deterministic in some sense, but they describe stochastic processes, stochastic behavior. So I want to say that my subject is very close to the talk of Richard Kerner, who was talking about stochastic matrices. Well, I would like to give some examples connected with stochastic matrices to illustrate my subject. Okay, so what is a stochastic? We have some measure space. For example, X can be a finite set or countable set, and we have some measure on this set. In the case of a finite set, this measure, it can be a counting measure. So the measure of a set is a number of elements of this set. And usually in probability theory, we have something which is called density. What is the density? It's a function which is positive, non-negative, and has integral 1. If we're thinking about finite sets, if X is a finite set, it's simply a sequence of numbers such that all numbers are positive, non-negative, and the sum of these numbers is 1. Okay? And what is a stochastic operator, or Markov operator? It's an operator which transfers densities into density. Okay. And you see, if we have some phenomena, some, for example, diffusion process or something like that, we transfer the distribution of particles into the distribution of particles. Or if in some biological phenomena, in some biological distribution models, we usually have some transformation of the distribution into a distribution. So stochastic operators describe such a transformation. Okay, and substochastic operators something similar. It is also an operator, a linear operator, which is positive, so it transfers positive function into a positive function, but the norm can be less than 1. And what is a stochastic semigroup? Stochastic semigroup is a simple set of stochastic operators which satisfy a semigroup condition. Here we have a semigroup condition. So in the language of our conference, it is some kind of monoid because there is identity here in this semigroup, and we have such a property. So one can say that this is a semigroup of where each element of this semigroup is connected with some non-negative real number. So, and we have some property of a semigroup. And the last thing is that we assume that such a function transfer functions from L1 by this semigroup is continuous. It's some assumption, some analytic assumption. But the most important thing is that we have this semigroup property. Well, and I would like to say something about the main subject of my talk. We are interested in the following property. First of all, if the semigroup preserves some function, so such a function we call invariant. So we have a transformation, semigroup transfer densities into densities, but some density is called invariant if it is transferred into invariant density. And what is interesting from the application point of view, if we have some invariant density, such that if we start from any other density and we transfer this density by a semigroup, then we finally goes to this invariant density. So this density is asymptotically stable. Why such a property is interesting? Consider some physical process, and you know that physical or biological process, you know that there is some invariant density which is asymptotically stable. So you have such a situation that you can start from any other distribution, but finally we go to this stationary distribution. So if the process is in a constant environment, then usually we can assume that the distribution is described by an invariant density. And the second property is maybe more strange, is sweeping. Okay, so what is sweeping from some set? If we have a sweeping property from some set, say B here, then it means that that the mass or the number of particles or something like that goes to 0 when times goes to infinity. So everything is swept from this set. Sweeping is something opposite to asymptotic stability. Asymptotic stability means that we are going to some distribution. Sweeping means that we are swept from the space in some sense. So you can imagine the following description. If you're preparing a tea, so you can put a bag of tea into a hot water, boiling water, and after some time, the diffusion makes that particles of tea are going around the cap, and finally we obtain some distribution of the tea. But if you consider the same process in a very, very large unbounded set, then the diffusion makes the particles of tea goes outside any set. So the concentration in some cell will go to 0. So it's a sweeping, so it's something different. And I would like to represent some results connected with asymptotic stability and sweeping. Maybe I change the shape. Well, I need to some definition here, but I explain this definition on this example with finite set. It will be the simplest one. When a semigroup is called partially integral, so here is the definition. If the semigroup can be bounded from below by some kernel part, so by some integral part. If you imagine a finite set or countable set, then all operators, all stochastic operators, all stochastic semigroups on countable set are integral. It's maybe strange because they act on a finite or countable space, but they are really integral. So like if you have a stochastic matrix, then this matrix is integral. It's a matrix, but it's an integral. Integral with respect to a measure, counting measure. So we have a very simple assumption concerning a semigroup that if we start from some point, say y, then we have some distribution. You can have some distribution. It's not a transformation from point to point, but we can have some distribution. And one of the main results in this direction is the following. If we have a partially integral stochastic semigroup, and this semigroup has a unique invariant density, then automatically, and this density is positive, then automatically this semigroup is asymptotically stable. So if we want to prove asymptotic stability of such a semigroup, you first should prove that there exists an invariant density. It is unique and positive. Then we have exactly such a property. So, well, but the main problem is that usually it's not easy to find invariant density. In some cases it's possible, in some cases not. And now I would like to present some results concerning the composition of the semigroups when we do not assume that we have invariant density at the beginning. We replace the condition that the semigroup is partially integral by some another condition. It is called K condition here. You see in the definition of partially integral semigroup, we have some kernel. Now we assume that this kernel has some property, some extra property, that it is estimated from below by something like that. What does it mean? That if we start from any point, y0, then we find some neighborhood of this point, then we transfer the distribution from this neighborhood in a similar way, so in uniform way. It's some estimation from below, like here. So this is a property of, say, K property. And this property plays the role in our investigation, but let me return back to the case when X is a finite or countable space. If the space is countable, then this property is fulfilled. So if we consider such a situation that we have finite or countable space, then without any other assumption, this is fulfilled. And now I would like to say something about the composition of a semigroup. So if we have a stochastic semigroup which has this property, this K property, not anything more, so we have this estimation from below, then we can divide the space into parts. It can be infinite number of these parts. So we divide X into parts. We have some set I, and in each set there is some invariant density. So the density is supported on this set. And if we restrict the semigroup to the action on such a set, then we have something like something similar to asymptotic stability, like that. And here is, so we have a convergence of density S to this invariant density on this set, multiplied by some constant. So it's not exactly asymptotic stability, but something similar to it. And so we have some number of such sets, and if we consider here the set Y, which is complement of this set, then on this complement we have asymptotic, we have sweeping property. So everything is swept from this set. So we have such a result. We have some decomposition of the space into some number of parts when we have kind of asymptotic stability and sweeping outside of these parts. And I will return back to this theorem because I try to give some corollaries from it, but some remarks. Instead of continuous time semigroup, because here is a time is continuous, is a positive real numbers here, we can consider a simpler iteration of some stochastic operator. For iteration, we have also similar property, but not exactly the same. We have something which is asymptotic periodicity. So instead of asymptotic stability, we have asymptotic periodicity. You can imagine a matrix which has the entries 0, 1, 1, 0, such a matrix. So if we take the second power of this matrix, then we obtain identity. And so we have a periodic behavior. We have not asymptotic behavior, but periodic. So for transfer for Markov operator or for stochastic operator, we can only periodicity. Well, now look once more at this result. Consider the situation that we have no invariant density, that we are able to check that we have no invariant densities. Then we don't have these sets, and we don't have this condition. So the space X is the same as Y here, if we don't have invariant densities. Then it means that we have sweeping from compact sets. because Y is a full space of the intersection of F and Y is a compact set. So if we have condition K and we are able to check that we don't have invariant density, then we have sweeping from compact sets. And the second, so the first corollary is the following, that if we have condition K and have no invariant density, then we have sweeping from compact sets. And the second thing is kind of irreducibility. What does mean that the semigroup is irreducible here? It means that if you observe this semigroup, then we visit all set here. So if you take any density, then this integral is positive. So it means that we can start the density which is concentrated on very small set, but under the action of this semigroup, this density is going on the full space. Then if you have irreducibility, then we have two possibilities. One is asymptotic stability or sweeping from compact sets. So such interesting property that irreducibility imply one of these two properties. And the last thing, if we have irreducibility, then if the space is compact, then immediately the semigroup is asymptotically stable. We will use this corollary after a moment. So this theorem about the composition gives us, maybe I will skip this thing, and I would like to go to some applications. Some results concerning application can be found in this book. It is connected with piecewise deterministic processes. What kind of animal is piecewise deterministic processes? Well, one of the general definitions are the piecewise deterministic processes are processes which are not diffusion processes. But there is another definition, maybe more precise, that if we have a process which is deterministic on some intervals, so we have a random times, and between these times we have, these times are called jumps, and between these times the process is deterministic. So we have something which is described in a deterministic way between some random times. Then this process is called piecewise deterministic. And there are two practically different types of piecewise deterministic processes. The first one is dynamical system with jumps. Can you imagine that we are going on the space, like here, and we jump from time to time in another position. So we have, from time to time, we have some jumps, some random jumps. So it's a dynamical system, so we are going according to some system of differential equations, something like that, and jump in the space. And the second thing is a process with switching dynamics. So we have different description of dynamics, but we change dynamics from time to time. So you have, here we have two different dynamics. One is described by these lines, and the second by that one. And we go according to some trajectory in one dynamics, then we change the dynamics we are going like here, and so on and so on. So you can imagine that you want to, you are moving somewhere, for example, in the space, and we want, so you are moving to some direction, and at some point you want to change direction. So you should start with an engine and change direction to go to another place. So we change dynamics. If you start with some engine, then you change the dynamics. And there are a lot of different applications of such processes. I wrote all of them here, but first of all, maybe for you, the simplest example is Markov chain. Richard Kerner was talking about some models connected with Markov chains. So we have a finite or countable set when you are going on this set and we jump from point to point. It's a Markov chain in some sense, or kangaroo movement. It's a more general situation. But there are also some different piecewise deterministic processes. For example, processes when we change velocity. So we are going to with some velocity, when we change it and so on. For example, we will consider a stochastic billiard. When we are going to the surface of this billiard, then hitting the surface, we change the velocity and going to another direction and so on and so on. Katarzyna will have a talk about semi-flows with jumps application into cell cycle models. I will say a few words about immune system. It will be of this type. And there are some processes used in the description of gene expression. There are processes with switching dynamics. We have different dynamics and we switch them from time to time and so on and so on. So there are a lot of different applications of such piecewise deterministic processes. And a few words about one example, gene expression model. What is gene are used to produce protein. Everybody knows that. But the process is not so simple. That first something happens in nucleus. There is a so you consider a cell. Inside of this cell is a nucleus. In nucleus is DNA, and DNA in the process called transcription produces some particles called mRNA or pre-mRNA. These particles are going outside nucleus, then a change here. So we have first pre-mRNA particles, then we have mRNA particles, and then finally, in another process, these particles, mRNA particles, produce protein. So we have some number of steps, starting in a nucleus, when active genes producing some particles, then in some steps we obtain proteins. And this processes depends on activity of genes. So gene can be active or inactive. If gene is inactive, then it does not produce mRNA particles. But if it's active, it's produced. So we have two different dynamics. One dynamics is connected with activity of gene, and the second dynamics is when we have no activity. And formally, we can describe this process in a very rather simple way. It's a linear differential system of linear differential equations like that. Here we have some terms responsible for production, RNA particles or proteins, these terms, and some terms connected with the generation of these particles. So, but from mathematical points of view, we have two systems of differential equations, which depends on activity of gene. This term is very specific one, A gamma of t. if gamma is 1, we have production of mRNA particles. If not, we have no production. So we change from time to time activity of gene. Here is a simpler version of this model. So you have a system, two systems of differential equation, which depends on this term. It could be 0 or 1. So it's a process with switching dynamics, because the dynamics is switched when gene is active to inactive, or from inactive to active gene. So generally, what is the connection with stochastic semigroup of this process? So, okay, we have 3 types of particles, like here. So it's a number of these particles is pre-mRNA particles, mRNA particles, proteins. But this is not a proper process. It's not a Markov process. It's very, in probability theory, it's very important to know that we have some Markov process. So we should add also here the state of the gene. So this process finally is a number of different particles plus the state of the gene. It could be 0 or 1. And we are interested in the distribution of this process. Here we have some distribution of this process, and this distribution is described by a stochastic semigroup. So the stochastic semigroup describes how the distribution is changing. So we start from some density of the distribution of these particles and the state of gene, and the semigroup describes the changing of this density. Well, a general situation is the following, that we have some number of system of differential equations, and we have jumps between these systems. So, and in the theory of semigroup of operators, the most important role plays generator of the semigroup. We have a continuous time situation is different than the semigroups we consider this conference, but if you have a continuous time semigroup, then generator is something like exponent in exponential function. So we have some differential equation like that, and in order to solve this differential equation, we can write this differential equation like exponential function of a times t. So generator is this exponent. So is that such a thing that we write this equation as exponent function of the generator. Of course, what does mean exponent function of such a thing is an operator, but generally it can be interpreted in such a way. So, and if we want to apply, for example, our theory to this subject, then we should check that we have some K condition. Okay. Well, I go to the second example. Dynamics of antibody levels. Now, everybody knows that the main problem with some epidemics is to take some vaccination and so on. But the process, if you have a contact with some epidemic, then you can gain some number, you can produce some antibodies. And we are interested in what is the distribution of these antibodies in your and this can be described also by a piecewise deterministic process. There are two papers. Here is a papers when they introduce some there is some introduction to this subject, and here is some mathematical process how to prove some results connected with production of antibodies. So, what is here a situation? We have two things. One thing is that if you have some number of antibodies, then this number decreases in time. So we have some differential equation which describe the decreasing of the number of antibodies. But when you have a contact with something, with epidemic, with infection, if you have some contact, then we produce some number of antibodies. So we have a jump. So usually the number of antibodies is going down, but from time to time, when we have a contact with infection, we have a jump. And so we have a, maybe it's some mathematics very advanced in some sense, but you should see, we have some differential equation, the simple differential equation which describes decrease of a number of antibodies, and we have a jump which increases them. And we can apply also this apparatus to such a model because it's a piecewise deterministic process, and one can prove some results on this subject. The result is the following. I will skip this description, but the result is the following. We have two possibilities. One is we have asymptotic stability. So the distribution of antibodies tends to some given density. So, of course, the process, if you look at a simpler man, then the process is changing in time. But if you look at the population, then we obtain some distribution of antibodies in the whole population. And there are some conditions which are connected with our model, which say when we have a kind of asymptotic stability. It can be simplified, this condition, when we have such asymptotic stability. But in some cases, we can have a sweeping property. It is very interesting what does mean sweeping in the case of epidemics. When there is such a property like here, it means that the concentration, so the number of antibodies, small number of antibodies in a finite, say, interval goes to zero. So it means that in time to time, antibodies, the number of antibodies goes to infinity. It can be connected with the term that the population will have asymptotic permanent immunity. So the sweeping property, very mathematical thing, can be interpreted in a very nice way. That is something like you expect to have permanent immunity of the population. So the population should be able to fit with epidemics in a very simple way. And whereas last example is some kinetic equation. I only want to tell a model. So we have some movement of particles. We have two planes, and particles are moving between these two planes. But they have a constant speed, one, but when they hit the plane, they can change the angle. The angle is not the same here. So we have only some transformation. It's a stochastic billiard, the simple thing. So we change only vertical coordinates of the speed. It can be changed into a one-dimensional billiard when the speed is a number from the interval -1 to 1, and we are going to one of this direction, and when we go to the end of the interval, then we change the speed in some random way, and so on, so on. So now we have stochastic billiard. This is a process where we have constant speed in some interval between jumps, but if we go to the end of the interval, we have changing of the speed. So it's another example, and we can prove some results concerning asymptotic stability of this process. It is very interesting that if I finish now, it is very interesting that if the distribution of the speed after the heating of the end of the interval is uniformly, if the speed is uniformly distributed in interval 0, 1, then we have no asymptotic stability. So it means that in this model, the initial model, sorry, the particles will not, for a very long time, will go from one place, one plane to another plane. So because vertical speed goes to 0, something like that. So as you see, using, first of all, with piecewise deterministic processes, we can describe many interesting phenomena, biological, mechanical, and so on. But the semigroup theory can be very useful to give some results concerning this phenomena. It's my conclusion. Thank you very much for your attention. Okay. So now I stop sharing the screen and I ask some of my collaborators and students to give some talks on this subject. The first speaker will be Katarzyna Pichur. She is from the University of Silesia, and she had a talk about application of the stochastic semigroups to cell cycle models. So please.
Okay, so thank you for introduction. As you said, I will talk about application of stochastic semigroup to cell cycle. My presentation is based on okay, so I talk about application of stochastic semigroups to cell cycle, and my presentation is based on our joint paper with Richard Rudnicki from 2019. The plan is following. First, I will a brief description of cell cycle. Then I will say something about stochastic semigroup, and finally, I will present theorem on asymptotic stability and sweeping of stochastic semigroup related to our model. And I compare long-time behavior in different models. So cell cycle is divided into 4 phases. The first one, in phase G1, we have a synthesis of various enzymes, and in the second one we have DNA synthesis. In G2 phase we have protein synthesis cars. And in the last phase, we have nuclear division and cytoplasmic division. Some models contains also extra phase G0, which cells have stopped division and has left cycle. In one phase model, all phases G1, S, G2, and M are treated as one. And another model is two-phase model. Biologists used to divide cell cycle into G1, S, and G2 phase. It is the first phase, and in mitosis phase. But from a mathematical point of view, it's better to divide cell cycle into phase A, which consists of phase G1. Phase G1 is called also resting phase because duration of this phase is random. And the second phase is phase B, which consists of S, G1, and M phase, and the duration of this phase is almost constant. We consider continuous and discrete time model. In continuous time model, we observe a sequence of consecutive descendants of a single cell. Each cell is characterized by age and maturity. Maturity can be size or volume or something like that. And here we have a graph which describe as maturity growth in resting and proliferating phase of mother cell and resting and proliferating phase of daughter cell. In discrete time model describes the relation between initial maturity of mother cell and initial maturity of daughter cell. Maturity structure model were investigated in many papers. One of the oldest is Rubinow model. In Rubinow model maturity describes the position of a cell in the cell cycle, and a newborn cell has maturity 0, and a cell divides at maturity 1. Maturity grows according to this equation. In Rubinow model, all cells have identical cell cycle. But for example, in the Lebowitz-Rubinow model, a maturation velocity is fixed at the birth and is constant during the cell cycle. So here we have the constant maturation velocity in each cell, but it is different in different cells or in different cell cycles. In Rothenberg model, maturation velocity can change during the cell cycle. The main topic of my lecture is two-phase cell cycle model. So we divide our cell cycle into two phases. One which has random duration, and second which has constant duration. And the maturation velocity is different in different phases. So in first phase, it is described by function G1, and in the second phase, it is described by function G2. So In our model is described by the cell from our model are described by age, maturity, and from some functions connected with move from the phase A to phase B, from maturation velocity, and from a maturity of the daughter cell. We assume that cells age with unitary velocity from 0 to tau A in the first phase, and from 0 to tau in second phase. And cell matures with velocity G1 in the first phase and G2 in the second phase. About this function G1 and G2, we assume that they are C1 functions. At the end of the first phase, a cell can move from the first phase to the second phase with some rate phi. About this function phi, we assumed that it is equal 0 belongs some minimum maturity, and it is positive above it. We also assume that such function Q goes to infinity as M goes to infinity. Here we have a rate at which we can go from phase A to phase B, and here is maturation velocity in first phase. So this condition means that that we must go from phase A to phase B. At the end of the cell cycle, our cell divides into two cells, which have equal maturity, and maturity of daughter cell is described by such function age. About this function age, we also assume that it is C1 function with positive derivative. So in continuous time model, we have the following jump times. By Sn, we denote the moments of entering of proliferating phase in end generation of cells, and by Tn, the moment of division. So we have the following jump times, and the state of the cell is described by age, maturity, and some index I, which is equal 1 when we are in the first phase, and 2 if we are in second phase. Before jump, our parameters change according to this equation in the deterministic way. So our process is described by piecewise deterministic Markov process. The cumulative distribution function of duration of the first phase is described by the following formula. Here we have function Q, and P1 is a solution of this equation. Our process is defined on the set, which is a union of two sets. Set X1 is connected with first phase and X2 with second phase. And here set X1 is bounded below by a solution of this equation started from point 0. But set X2 by this solution started from the minimal maturity. It's a minimal maturity at which cell can move to the second phase. If we assume that our process at point 0, time 0, has density, then after some time, the process ct has also density. And in this way, we can introduce the stochastic semigroup. So our stochastic semigroup describes the evolution of density, as Richard said in his talk, of course. Discrete time model. In discrete time model, we have some operator which describes the evolution of density. So if F is density of the initial maturity of mother cell, then PF is a density of initial maturity of daughters. All functions are listed above, but here we have function lambda. What is lambda? Lambda is inverse of some function psi, and psi is maturity of daughter cell is if mother cell has maturity M at the beginning at second phase. And lambda is inverse of this function. Function Q, we know function Q was introduced earlier. And this operator is stochastic operator. What is stochastic operator? Stochastic operator is such operator which preserves the set of densities. And density is L1 function, non-negative with norm 1. Continuous semigroup of stochastic operators is called stochastic semigroup. It should be noted that also powers iteration of operators or of stochastic operator also forms the semigroup, discrete semigroup. Okay, so now I will recall some notion connected with semigroups, with stochastic semigroup. So we say that stochastic semigroup is asymptotically stable if there is invariant density. Invariant density, such density doesn't change under acting of operator PT, such that PT of F goes to this density, ST goes to infinity, and of course in norm L1. Opposite notion is sweeping. We say that semigroup is sweeping from some set B. If such integral over set B goes to 0, ST goes to infinity. The next notion is partially, we say that semigroup is partially integral if there exists some kernel non-negative, such that PT of F is bounded below by this kernel part, and we have theorem that semigroup, that partial integral stochastic semigroup, if partial integral stochastic semigroup has invariant density and this density is positive, then this semigroup is asymptotically stable. But as Richard said, the main difficulties with applying of this theorem is that it's rather difficult to find this invariant density in biological examples. And notion K, we say that stochastic semigroup satisfies condition K if kernel part is bounded below by such formula. Here we have function eta. About eta we assume that its integral is positive. So Shell explained this notion, so I skip here. But another notion is overlapping support. So we say that stochastic semigroup overlaps supports if for some T, measure of intersection of a support of such operator is positive. And for continuous or discrete, no matter what, semigroups, we have the following two theorems, theorem 2 and theorem 3. If our semigroup discrete of continuous satisfies condition K and has no invariant density, then it is sweeping from compact set. And if our semigroup satisfies condition K and overlaps supports and has invariant density, but this density has but a complement of supports of this density is a subset of compact set of, or it is compact set, then our semigroup is asymptotically stable. So if we investigate discrete semigroup related to our model, then this semigroup satisfies condition K and overlaps supports. So if it has no invariant density, then it is sweeping from compact set. But if it has invariant density, then this density satisfies this support condition. So we say that discrete semigroup satisfies Vogel alternative. It is asymptotically stable or sweeping from compact sets. As I said, theorem 2 and theorem 3 is true for discrete and continuous semigroup. But in case of continuous semigroup, we have the following theorem, the following decomposition theorem. Richard said more about this theorem, so I will recall only the most important thing. We assume that our semigroup, our continuous semigroup, satisfies also condition K. And our space is divided into two parts. In one, we have supports of invariant densities, at which where we have something like stability, something like asymptotic stability, and we have sweeping beyond this set. So, if our semigroup has no invariant satisfies condition K and has no invariant density, then this set is empty set and we have sweeping. But if our semigroup has invariant density and supports of this density on complement of the support of this density, we have sweeping, this integral goes to 0, then our semigroup concentrate on the support of density, of this our density. And our semigroup is stochastic, and in this so alpha, functional alpha must be equal 1, and in this case we have asymptotic stability. So in the case of when our semigroup is continuous, then theorem 2 and theorem 3 is a simple consequence of this decomposition theorem. We proved that in the case of continuous semigroup, that continuous semigroup also satisfies Vogel alternative. But in this case, we have to assume two additional conditions. The first one is rather typical. It means that that maturity of daughter cell is less than maturity of a cell and the beginning of a second phase. This one looks complicated, but if we have, but if in both phases we have equal velocity, maturation velocity, and if our cell divides in half, then this condition has this form, and in this version, it has been assumed in many times in many papers. We prove also the following theorem, which compares the long time behavior of a discrete and continuous semigroup. So if a discrete semigroup is asymptotically stable and a function and rate phi is greater than some positive epsilon for sufficiently large m, then also continuous semigroup is asymptotically stable. And if our discrete semigroup is sweeping and function phi is bounded, then also continuous semigroup is sweeping. But we know when discrete semigroup is asymptotically stable. So if following inequality holds, then our discrete semigroup is asymptotically stable. Alpha is given here. And similar for sweeping. So if we here add assumption, this assumption, then we obtain condition for at which our continuous semigroup is asymptotically stable. And the same thing with sweeping. So in this way, we obtain condition for at which our continuous semigroup is asymptotically stable and sweeping. But what is very interesting, that we can show example then that discrete semigroup is asymptotically stable, but continuous semigroup is sweeping. In this case, of course, such condition, this condition doesn't hold, and phi goes to 0 as m goes to infinity. And we also can show example when discrete semigroup is sweeping, phi is unbounded function, and continuous semigroup is asymptotically stable. This condition means that the rate phase or the rate of the entrance of the second phase. So this rate is very small for large m, and the length of cell cycle is very, very big. So thank you for attention. Is all, and bibliography. And thank you.
Let me start the second part of our session. The next speaker will be Andrzej Tomski. He is associate professor at the University of Silesia in Katowice. So please start your talk.
Dear sirs, good afternoon. Thank you for invitation. I hope you won't be disturbed because you can hear in the background that somebody is drilling. and I don't have any influence on it. So sorry, I hope it will be bearable. Okay, so let's start with my talk. Okay, so let's put it on the full screen. So the title of my talk is randomly switching evolution equations with applications. And this is joint work with Paweł Klimasara, Michael Mackey, and Marta Tyran-Kamińska. So I have the duty and the honor to represent all of them during this conference. Okay, so I'm not there like in person, but I'm thinking about the place. So I found this monument, and I found that this is a monument of liberators of Nice. Am I right? Am I right? It's a monument of liberators of Nice.
Just a moment,
Yeah.
Yeah, you are right. It is the monument on the very center of Nice, and a very old monument to the liberators of Nice during the wars, previous wars, first and even further in the past. So thank you very much for sharing this picture with us. And I do hope you and all of your colleagues will come soon and that we will make a picture in front of this monument.
Yes. So I found it, and because let's say we have something similar in Katowice, because this is a monument of Marshal Józef Piłsudski, the last marshal of Poland, almost 100 years ago. So there are some similarities. Yes, I always think that Serbia and Poland are quite similar countries. In fact, to very huge extent. Okay.
Slavic people.
What? Sorry?
Slavic people, after all.
Slavic people, yes. Yes. These are my collaborators. Current leader of the group is Marta Tyran-Kamińska. She is a student first of Professor Andrzej Lasota and then of Professor Ryszard Rudnicki, and she's now the leader of our group. She is still strongly supported by Michael Mackey, which is quite well-recognized American biomathematician. And our third collaborator is Paweł Klimasara. He currently working in Rzeszów. It's another city in the south of Poland, and he's interested in mainly in correlated particles physics. So this is our group. Okay. What was our inspiration? It were the works of Paul Breslov, which was titled Stochastic Dual Equation for Particles Driven by Dichotomous Environmental Noise. So if the one is interested in this topic, or will be ever, then rather I would say but don't start with our work, because our work is quite formal. Rather start with intuition. So Breslov as a physician is a good thing to start with. We also use results from papers, and later they were all selected and they were put into book Piecewise Deterministic Processes in Biological Models. And so these are the two positions I would say the one should start with. So when it comes to introductory work, we have papers by Breslov, but he works with Lowley, Reed. This is, I call it Utah group. So let's say that predecessors of this topic there are people from Utah, and later we continue this, and let's say we extended this topic with putting special care to semi-groups. So there will be semi-groups, and let's say these people rather don't use semi-group language in this problem, while we use it a lot. So we use okay. So low layer, I would say it's, of course, all of these people are very interesting, but for my personal impression and my personal point of view is that especially Lowley is a very interesting person because he is, let's say, similarly my age, and he has done and he has published almost 100 papers, let's say, with similar, in my opinion, of course, level of difficulty. So he and so I suppose he is very, yes, he is very interesting in the sense that his work, let's say, at this moment of his career, let's say, it's quite amazing, I would say. So that's one person I would say the one who would be interested with this topic should be familiar with. Okay, so what are the highlights of this paper? Let's say what we are talking about in nutshell. Motivation is to analyze the dynamics of a population of non-interacting particles in the presence of an environmental stochastic input. This leads to investigation of stochastic evolution, in which a family of evolution equations in L1 space are driven by some continuous time Markov processes. These are examples we will see of the so-called piecewise deterministic Markov processes on the space of integrable functions. And as some of you know for sure, some of you will see it leads to Markov semigroups. And we investigate moment of this process and its long time behavior. We show examples of this process in science, especially in biology and physics. Okay, so let's start with an example. Yes, so what is a population under environmental input? So here we have possibly very huge number of particles, a particle population who are of yeasts, who are let's say influenced by some kind of environmental input perturbation. To be more strict, these are the single-celled Saccharomyces, and authors of the paper in the journal, they ask what is the response of the single-celled yeast metabolic system to randomly change environmental stimulus. So let's say we can imagine that we think about population which reacts somehow to randomly change environmental conditions. And let's say this change affects all the population and all possibly given parameters of this population. So let's say that's a problem when it comes to biology. How we deal with such problems, and how we dealt with it, how did we proceed before? So some people should know that there is a Liouville equation for density evolution in very simple case. Let's say we have a point in R to the power of n space, and we consider typical simple Cauchy problem. Yes, this is simple Cauchy problem, differential equation with initial condition. And as we see, we consider, let's say we consider the movement of points given by this differential equation. And the sense of it is that we look at this movement statistically. So we consider evolution of densities. You see the initial density is denoted by F, while then later it's denoted by rho. This is the density. And we consider evolution of densities of distribution at this point. And this is what this equation, the last one, yes. So the equation you can see here with the presence of the divergence operator on the right hand side. This is called UV equation. I suppose most of you know it. So, but this is a classical approach, and of course there are plenty of models which we are interested about the dynamics, and we can very simply denote, and we can very simply write UV equation model of two-stage gene expression, which I could suspect my predecessors, as you saw, they mentioned this model. So we can consider concentration of some particles level, let's say proteins at time t, and we have a state of a gene. First, if as the state is a deterministic function, it's just a deterministic dynamic. So this is typical thing which can be described by UV equation if this deterministic, at least now. Yes. So we, for example, this is the picture two-stage gene regulatory network. Some of you can be familiar with it. Some of you may be little bit less. But as you maybe know, the whole process of gene expression, it starts with the binding of transcription factors to the special site of a gene, and then the whole process, the pre-mRNA, RNA, and protein processing comes and follows, and then we observe what is going on with the level of the particles. If in the simplest model, when the dimension is 1, we only observe the simplest case. So when there are only proteins, despite the fact we know that these types of particles, there's plenty of types of particles, mRNA, pre-mRNA, and much more. But to do not lose our sight, and to stay with its simplicity, first we only consider proteins. So we know this process is considered, yes, and we can make it stochastic, because I said that the state of a gene is constant, but we can make it stochastic. We can do it, and we can introduce stochastic process which makes that this gene state switches with some given intensity. These intensities, that they are denoted K plus and K minus. I will describe it in a while, but this is a stochastic mechanism that can be introduced here. So as you see, we can switch between two states with the intensities K1 and K0. Most of the people, when I showed this to most of the people, and especially most of the mathematicians, they are confused because they totally do not understand what this scheme shows, because this is a scheme which is known rather from chemistry, yes, reaction scheme, not let's say system of equations. We know from many various kinds of mathematical problems. But let's say I will show it. But let's say the explanation is that these switching intensities influence the distribution function of the intensity the process stays in one of the time. They influence the distribution of the time the process stays in one of these states. We will see this, how it looks in a formal way, in a while. This is just, let's say, more intuition than mathematics. Yes. So what? But very important question is, what is this stochastic disturbance? What is it? Which kind of stochastic process is it? Most people think this is a normal disturbance, while it's not. It's PDMPs introduced by Mark Herbert Davis in 1984. Unfortunately, he died last year. So let's say we continue his work and contribution to this field. So PDMPs are a very broad family of stochastic models covering most of the applications, let's say omitting mainly diffusion-related phenomena. This is the most general definition. PDMP is a Markov process with continuous time and values in symmetric space. This process evolves deterministically between the so-called jump times that form an increased sequence of random times. However, and this is quite important feature, at least of this PDMP, at the jump times, one considers a different type of behavior, such that there is an actual jump to a different point in the phase space or a change of the dynamics. In our case, we are interested in this in the latter one, the situation. So in the case when a change of the dynamics occurs, however, as we see, it's not the only possible case. But we can think about it that when we model processes by PDMP, that the most recognizable models describe situation when each switch, stochastic switch of a state of the gene just means that there is a change of the dynamics of this process. That's how we can think about it. And a typical piecewise deterministic Markov process, what I want to start with, is it happens in, let's say, metric space, but till, let's say, maybe I'm not right, because I don't have so huge basis of all the papers that appeared about piecewise deterministic Markov processes. But let's say the typical particle approach, which was popular, let's say 10 or 5 years, or even 5 years ago, it was piecewise deterministic Markov processes on R to the power of n space. This is in fact, it's Cartesian product, R to the power of n. In the simplest case, it's R multiplied by a Cartesian by a Cartesian product with 0, 1. But the 0, 1, it's this element of the state space which describes state of a gene. So this is a product of the state space. The state space of a Markov process is a product of deterministic part of the state space. This is this R, and the state space of this, let's say, stochastic part. This is a gene state. So in fact, a state of a gene in this process is described by two quantities. Yes, the first one is this deterministic part from the space of R to the power of n, and the second part is in fact the state of the gene. Is it active or not? But of course, it can be extended to multiple states. For example, it can be a state between the active and inactive state. There is no limit. Let's say in most of the papers they say that the state space should be at least countable. Yes, but most of the people even reduce it to finite case. But what about population perspective? So because here we can see that we consider the process in a particle regime. What does that mean? In fact, we can explain this phenomena from the point of view of a single individual. I will come back to it in a while, but we can also explain the same phenomena in a situation which the entire population is affected by randomly switching environmental conditions. So and then we come to think what is the state, but in the sense and in the meaning of the density. So here you see that we can think about a single individual. So when the dynamics of each individual is driven by some stochastic laws depending on some parameters, but the second regime is when we think about entire population randomly affected by randomly switching conditions. Yes, so the whole population is driven by a common environmental noise. And the second case is the case we are considering. But what is a trouble with this perspective? What is the trouble with this approach? So the whole population is affected by some continuous time Markov process. So we can define a PTMP in this situation. So, but here we have a finite state space that change the current state of all individuals. And here a state is represented by a population density, the population density of this particle. So not an element in the R to the power of n, or in a other quite nice finite dimensional space, but now it becomes an element of an infinite dimensional space, a density, space of densities, space of functions from L1. This is the trouble, yes, because let's say in general the precise theory for evolution of such densities is not known to this extent as it is well known when it comes to processes in R to the power of n. It's quite more difficult. So the trouble is how to study the evolution of such densities. Let's look closer at least to the moment of such processes, because sometimes, let's say, we can find some connections between moments of such processes and the results from classical approach. You will see that for example, the stationary densities from the class you can find in classical approach can be approximated by means of this process in L1 by means of this process for sufficiently long time. And just to mention that our work is in fact based on the results done by Grigo and Hersh random evolutions. Yes, so let's say they consider quite dual problem to our problem, because we did it in L1. They consider processes in L to the power of infinity, and this was inspired also by telegraphic equation considered by Goldstein and Katz. So you will see that some sources appeared even earlier than the full and formal definition of PTMP come around. So it's quite a long history, but these are the let's say very special cases of these processes of PTMPs. Possibly these people do not know, of course, that and they were not aware that this will be classified in such a way. Okay, so we come into classical perspective. The classical perspective can be called randomly switching dynamics. So if we consider vector fields defined on an open subset G of R to the power of D, E is a Borel set with some assumptions, as I denote here, and we have a differential equations, yes, driven by these vector fields with some initial condition, and what is important, it has a solution. And if we have a density of e-valued random vector, then the density of the solutions of this equation for this in a time for a given time t, and for this when we start from this random value samples from this random vector, can be given by a semigroup. And this semigroup is well known that the semigroup has an equation, has a well-known formula. It's Frobenius-Perron semigroup, and stochastic group, Markov semigroup as well. So randomly switching dynamics leads into a Markov semigroup, we see. And even we can denote the equation. I put here all the formalism, but the most important thing is randomly switching the dynamics is a Markov process on a space given by some differential equation with the switching process, which is a continuous time Markov chain with values in I and the intensity matrix Qij. And in general case, it's a whole matrix because we can have multiple states of a gene, but you can connect this intensity matrix with this K1 and K0 from the reaction scheme I showed you before. Yes, but in general case we know it by QI. So this is the place, and this is the part of this formula where these intensities appear. And then if we have a stochastic semigroup, Frobenius Perron, as we saw in the previous equation, and if we have its generators for each single state I, then if we define a semigroup, a semigroup on these spaces, on each of these spaces for each single state, then the operator A, where A, as we see, is given in this way, and Q is this matrix and this intensity matrix, then the operator R plus Q transpose is the infinitesimal generator of a stochastic semigroup. And if we define U in terms of this semigroup, it appears that U satisfies such evolution equation. So as we see in a general form, we have so if we start with some density, then the evolution of this density can be described by this semigroup, which has a well-known generator. Okay, so what is the randomly? We saw what is randomly switching dynamics, but what are randomly switching densities, or what is randomly switching densities as a theory, as a single theory? So let L1 be a space, yes, with E rho separable metric space, M is a sigma finite measure, and if we have a generator of a stochastic semigroup on L1 defined on this space E, and if we assume that the stochastic process is continuous time Markov chain with state space I and constant intensities, because we did it, we were able to prove the result with constant intensities, because these intensities don't have to be constant necessarily, but in this regime they are. So if we consider the following stochastic evolution equation, this one, so we have the generator of this semigroup. Let's use. You can see that this time I is connected and joined, and let's say it's linked to the stochastic process I. So this is the stochastic evolution equation, which means that this time we switch generators of the semigroups, not the states, not the dynamics. Yes, so not the systems we are using before. This time we switch generators, and such equation generates a well-defined PDMP, but this time it's not in space R to the power of n crossed by I, Cartesian way, but this time it's a PDMP in the space L1 multiplied in a Cartesian way by I. So this is a new PDMP in new state space. Okay, so I will not describe in details, but here you can see how did we define a semigroup, which is the solution of this equation. But you can define a stochastic semigroup, which is a solution of this evolution equation. And now we can see how that works, how it works for some special examples, and we will see how this evolution follows. So first example is a population model with different birth rates. So we have a population of size of some assumed size, a death rate U, and birth rate B minus CX will be changing between two possible values in response to some environmental disturbance, and the growth of the population is assumed to be determined by these two differential equations. So as you see, what changes here is this beta parameter. Yes, this is what changes in fact for these two systems, and for each value of I, equation 1, this was the differential equation I put at the beginning. This, for each value of I, of course, this equation, as we know, induces a stochastic semigroup. We know this from the beginning. If the population grows initially with birth rate related to some value of I and has a distribution density G, then after time t greater than 0, the population distribution density is given by the evoluted value of G with respect to this semigroup. And we consider the switching, in fact, between semigroups according to a Markov chain, and then we obtain a stochastic Liouville equation. So now it has the stochastic component, stochastic process, as you can see on the right-hand side of this equation, and ut of x is defined with the respect to the semigroup, and this is the u which is given by this Liouville equation in the stochastic form is the population density. Another example, and this is an example which my successor, Mrs. Kozdemba, will say, it's a Goodwin model, but while she will describe it in 2 dimensions, I use 1-dimensional version, and this is a model which describes the expression of genes driven by positive feedback, control of gene transcription, and we can look at the cluster of identical copies of a gene, and if we denote by X the concentration level at time t, and by gammas degradation rates corresponding to 2 states of this gene, this is a differential equation we can write here, and where n is a parameter, and as we know, again, this equation of course induces a semigroup as in formula in the beginning, and if the gene cluster has a degradation rate gamma for I and a distribution density G, after time t, the population distribution density is given by the value that G has evolved under influence of the semigroup Pi. By taking Bi in the Liouville equation by taking Pi in the Liouville equal to the right-hand side, by taking Pi in the Liouville equation equal to the right-hand side of equation 9, we obtain the stochastic Liouville equation again, again, in the similar manner as in the previous example. Okay, so these are the examples. I will show some numerical simulations, but what we did in fact. So in a nutshell, so using a simple decomposition, we can find the first moment of U in the stochastic Liouville equation. This is the formula, where here, as we can expect, E denotes the expectation, and this φ1 is the indication function of an event. So this is the formula, in fact, for first moment. These sums are with respect to the states, yes, from the intensity matrix, because J and I are the states of a single let's say the states of a single item. So if we define L1 on the product E times I with the product of the measure and the count on E and the counting measure on I, then we have the family of the operators on the space L1, which was mentioned before, given by this formula, by formula 10. And we had to assume two technical assumptions. For example, yes, if Pi is a stochastic semigroup with some generator AI, and for each I there exists a C0 semigroup on B such that it commutes in the sense of equation 12. So Pi and Ti commute in the sense of this scalar product, which is defined by an integral. Then we proved the following theorem. Under these two conditions, the family of operators defined in formula 10. So just to mention it, this family of operators defined by this formula is a stochastic semigroup on the space L1, defined as before on the space E product Cartesian product E times I. Moreover, we found the formula for the generator of this semigroup. It is I plus Qt, where A we can define with the help of the generators for each state given before. So second thing, this is the first thing. So this was the formula. So the 10 was the formula for the stochastic semigroup on this space. But what else can be said if PT is given by this equation I showed you before, and UT, let's come back for a while. UT is the solution of the stochastic evolution equation for each G and I, such that U starts with G and I start with some given state. We have VI, so VI is given by this semigroup, and we found a formula for the mean of the process. So the mean of this process, this piecewise deterministic Markov process in L1 space, is given by this formula. We see the sum with respect to all states of these semigroups, which were given in the equation 10. Yes. Moreover, if for each I, for each state, there exists a density Fi such that we see Ui converges to Fi in a, let's say it converges in a Lasota sense, this integral convergence, then we have that this Vi converges to F as well. so where and VI converges to V with the star, where V with the star is the sum of these I with the star. So these densities and the function V star is called the mean of the process of at large time. So what is the conclusion? We can express the mean process of at large time with these functions Fi. So in fact, with stationary densities of the process. So in particular, this condition, which is given here, holds if semigroup P is asymptotically stable. So there exists such a density, it's called invariant density, such that the densities which evolves according to P, these densities converge to this density in this Lasota sense, and this is called, and this density is called an invariant density. Another property is sweeping, which is in some way contradictory to asymptotic to the asymptotic stability property. It means, as you can see, that this integral converges to zero when t goes to infinity. And this means that the mean of the process at large times is equal to 0. So we have found a connection between the invariant density in the classical regime at the mean of this process at the large time. So rather, because of the lack of time, I will not describe here all the details and all the conditions which are known and which were introduced by Ryszard Rudnicki to investigate asymptotic stability and sweeping properties of randomly switching dynamics processes in quite effective way, but I will conclude it with the result that we are able, thanks to that, we are able to estimate mean of this process at a large time. And what I want to show you in the end is that these are the numerical simulations of the mean of the processes I mentioned before. So example 1 is the process I denote here. So it's a population model with 2 birth rates. Here, under sufficient conditions, we can see that that the densities of this process for some given values of the parameters converges to the stationary density, which corresponds to this process from this system of evolution equations, from the evolution equations for randomly switching dynamics. So we can see here that within time, these densities converges to the stationary density, as we can see, of course, for such values of parameters that satisfy all the conditions that are needed for the semigroup to be asymptotically stable. So let's say the main, just to conclude our result, we studied the first moment of the stochastic evolution equations and found the correspondence between this moment equation and the deterministic system of Fokker-Planck. But let's call it evolution because I did not use it before. So Fokker-Planck, let's call it evolution type equations for the distributions of the process in Euclidean state space. We concluded then that the mean of the process at large times can be expressed by stationary solutions of evolution equation, for classical evolution equation, as it's called Fokker-Planck type system. Similarly, we connected the mean of the process at large time with sweeping property. What I did not show, but I will just mention, we studied also second-order correlations of solutions of the stochastic evolution equations, and we provided a rigorous way to extend our considerations to correlations of higher order. But these are the moments, yes, the moment of correlations, the mean, the moment at large time. But the question is, at the next step would be to show convergence in distribution of the infinite dimensional process from this stochastic Liouville or stochastic evolution equation to a stationary distribution. And that is an, let's say, open question. So that's all. Thank you.
Okay, thank you. So we go to the last talk. It was given by Agnieszka Kozdęba. She is my PhD student from Jagiellonian University in Kraków. So please start your talk.
Good afternoon. Thank you for introducing me. Could you hear me well?
Yeah, we can.
Okay, thanks. Okay. I have no interesting monuments to show, but I can show you a view from my window, current view. And today I will talk about some application of stochastic semigroup, application of the Goodwin model to autoregulatory feedback for stochastic gene expression. And this presentation is based on a paper under the same title written by me and previous speaker, Dr. Andrzej Tomski. And after all previous speeches, we already know a little about gene expression and piecewise deterministic Markov processes. So let us take a look at this scheme of gene expression to precise what kind of model we will study now. We consider gene expression, two stages of gene expression, mRNA processing during the transcription phase and translation, which leads us to the synthesis of proteins. And here we have a feedback loop with some protein-regulated transcription rate. And the gene also could be active or inactive. We have some switching intensity function and some coefficients, production rates and degradation rates. And as it was said, piecewise deterministic Markov process is some continuous time Markov process with some sequence of random jump times, and this process in some interval is described by a differential equation, and it is deterministic. And some moments there is a jump and dynamics change. Typically, the gene regulation process is modeled by some reaction rate system of differential equations. Here we have this regulation function f. But in 1965, Goodwin introduced proposed a model with Hill function as this regulation function. One can consider either decreasing and increasing Hill function. We start from decreasing Hill function. We can show it on the graph for different values of parameter n. And this type of regulation function leads to a negative feedback loop. So our system, we can introduce now X and Y denote the level of concentration mRNA and proteins respectively. We have some initial condition and the following system of equation described this model. All constants are positive and have the same meaning as in the previous scheme. We have here also this switching intensity functions and some random function gamma of t, which is equal to 1 when the gene is active, and when the gene is inactive, it is equal to 0. After some simplification, we can write the system in that way, and we'll analyze it in that form. Now, let's take a look what happened in these two situations, the active and inactive gene. First, what happened when I is equal to 0, so the gene is inactive. Then the system takes the following form. It is simple system of differential equation, and it's easy to see that this system has only one stationary point in point 0, 0, and this point is globally asymptotically stable. And here one can see sample solution trajectories of this process. All trajectories goes to 0. It is when the gene is inactive. When in the second case, when the gene is active, system takes the following form, and this system also has a single steady state, which need to satisfy the following system of equations, and this steady state is also asymptotically stable. So in two different situations, we have two different steady states, asymptotically stable steady states. In this picture, we can see solution of the system in these two cases. And any state of the system we can denote by a triple X, Y, I. And when we are at some state, the process can behave in two different ways. It can it can reach the state pi minus of txi after some time t, or it can we can have a jump. The system can switch to the state with, if we have in 0 state, we are in 1, or the other side. Here we have more formal definition of random function gamma of t, where Tn are these jump times for this system. There are moments in which we are changed dynamics, and if we have this random function, this triple x of t, y of t, and gamma of t constitutes a piecewise deterministic Markov process for the system with negative feedback loop. We can introduce analogic system for increasing Hill function, which we have here again an example for different values of n. And when the Hill function increase, then it appears positive feedback loop. And again, we have a system of equation, and in this model, all symbols of constants have the same meaning as before. And the only difference is in a regulation function. Here we have this increasing Hill function. And again, we can simplify the system, and we denote unique solution by pi with plus of t x0 and I. Again, we have two possibilities of behavior of the process, and we can define gamma of t in the same way, and then the triple x, y, and gamma with t greater than 0 constitutes a piecewise deterministic Markov process for this model. And again, for different states of a gene, we have different situations. When the gene is inactive, the model has exactly the same form as in the negative case. We again have only one stationary point in 0, 0, which is globally asymptotically stable. But when the gene is active, the situation is more complicated. And now the number of stationary points will depend on the values of coefficients. Stationary points need to satisfy these equations, and we can have 1, 2, or 3 steady states depending on the values of coefficient. But we are interested in only this case when we have 3 steady states. Of course, one of them is also 0, and it is again global asymptotically stable point. But it is also appear saddle here, and another stable point, but only locally asymptotically stable. In this picture, we can see sample trajectories of the system and observe these 3 steady states. So now this is the model, and now we want to analyze long-time asymptotic behavior of this model and of its piecewise deterministic Markov process. So we can formulate the following theorem. First, for negative feedback. If we have this stochastic process for the system with negative feedback loop, and we have this switching intensity function are positive for any given point, then the process, the stochastic process, has a unique stationary density, and the density of the distribution of the process is convergent to this stationary density for any initial distribution. And moreover, this stationary distribution is concentrated on some set, set A, which is contained in set A, which is illustrated in this picture. This set, as you can see, is bounded by some trajectories of this model. For positive feedback, model with positive feedback loop, the situation is a little different, but because here, if we have this stochastic process and this positive function qi, then for n epsilon and a positive epsilon, the probability that concentration of mRNA and protein is greater than that epsilon converge to 0 when times go to infinity, which means that the process given by the system, for this process, the number of both mRNA and protein decreases to 0 with time. And these theorems and both these theorems we can reformulate and prove using the notion of Markov semigroups. And here I have basic definition, which we have seen today many times. So I'll only quickly remind that we have Markov operators and family of Markov operators called Markov semigroup under this condition. And in one model, one model is connected with asymptotically stable Markov semigroup, and the second model is connected with sweeping Markov semigroup. So we can see in a minute. Here I have one more theorem from theory of Markov semigroup. When if for some Markov semigroup are satisfied some condition, which I presented in a moment, then this semigroup is asymptotically stable. Here we have this condition. Some of them we showed before and seen before. But you can interpret this condition in some more simple way. The first, for example, means that there exists in our situation there exists a some state such we can get anywhere close to this point starting from any another state. The last condition means that for some point x0 we can it means it means that there is no sweeping from compact sets for our model. And okay, and we can reformulate these theorems which are shown before using the notion of Markov semigroup. So for negative feedback case, we have the Markov semigroup generated by the stochastic process of this model, and we have this switching intensity function, which are positive for any given point. Then the Markov semigroup is asymptotically stable, and support for the invariant density is contained in the set I presented before. To prove this theorem, we can use one more remark on theory of Markov process. No, not exactly, but yes. So we need to find a family of increasing sequence of bounded open sets, which fulfill some condition, and check that this product is smaller than 0, and then the solution of our system, then we know that solution of our system will remain in the sum set, and it gives us that these sets are invariant with respect to the semigroup. So I have here a short sketch of the proof, this theorem. So first we, as I said, we need to find this family of bounded sets, and it has such a form. And after some calculation, we can show that that really assumption of the previous remark are fulfilled. So for I from set 0, 1, these sets are really invariant for the semigroup. Next, we need to check Fermander condition, which we also can see in the previous speech. And when Fermander's condition holds at some point, then the condition K is satisfied also. And the last thing is condition Wi, and it holds if there exists some state such that starting from any state of the process, we are able to go close to this point, using trajectories of the process. But the point 0, 0 is asymptotically stable stationary point, so we are able to come arbitrarily close to this point, and it means this condition holds. These three things gives us that that semigroup is asymptotically stable, and set A times 0, 1 contains the support of the invariant density. I think it's quite obvious that if in a negative feedback case we have asymptotic stability, in positive feedback we have sweeping. So one can observe that the behavior of this process corresponds to the property of sweeping, and the theorem of for positive feedback we can reformulate in the following form, that for semigroup, Markov semigroup generated by the stochastic process, this semigroup is sweeping from the family of all compact subset of R square plus. And again, to prove this theory, we need here we need two things. We first need to show that almost all trajectories of the process, stochastic process, approach arbitrarily close to the point 0, 0. And the second thing, we need to find a family of sufficiently small neighborhoods of the point 0, 0, and which are invariant set for both of the semi-closed, for both cases when I is equal to 0 and when I is equal to 1. And this set becomes invariant, and this will imply that the semigroup is sweeping from the family of all compact subsets. Okay. Because the point 0, 0 is globally asymptotically stable for this system, for both case 0 and 1, one can easily show the first point, and in the second point we also use a remark presented before. We consider the family of set defined in the same way as before, and the normal vector, and after some calculation we obtain that that for sufficiently small k, that family of sets is invariant for our stochastic process. So the semigroup is really sweeping from the family of all compact subsets. And now I want to show you some stochastic simulation for our models. First, for negative feedback. Here you can see some trajectories, two-dimensional trajectories of the stochastic Goodwin model with negative feedback for different value of parameters. The horizontal axis represents the concentration of mRNA molecules, while the vertical axis represents the concentration level of protein. And we can clearly see on in this picture the form of our invariant set A. And here also we can see estimation of stationary densities for this stochastic Goodwin model for negative feedback. Two more examples for negative feedback loop, trajectories and corresponding stationary densities. And here I have comparison of trajectories of the stochastic process with negative feedback loop and positive feedback loop. Left, we have negative case, and right on the right, positive case. For exact same parameters, and it's easy to see that in positive case, trajectories in some moment goes to 0, while in negative case we have this invariant set. And here's some simulation for positive feedback. Again, for different values of parameters, two-dimensional trajectories, and corresponding stationary density, and two more examples. And that's, I have maybe 4 minutes, but that's all what I want to show you. So thank you for your attention.
Thank you very much for your talk. So I would like to summarize what we are doing. First of all, if we want to study some real processes, we should, using mathematical tools, we should find a proper mathematical description. In our case, we mainly interested in some processes which has some hybrid structure. Most of biological processes and physical have such a structure that they have some deterministic part and stochastic part. So if we are able to describe it in a proper way, for example, by using so-called piecewise deterministic processes, then usually we are able to find some proper space and some stochastic semigroup, which describe the evolution of distribution of such processes. What is a stochastic semigroup? I will recall simply. It's a semigroup which transfer density of the processes in time. So we have some initial distribution given by a density, and we describe what is going on with this distribution in time. And what is the most interesting from the application point of view? First of all, the existence of stationary distribution or invariant distribution, invariant density. The second thing, convergence to with invariant density. It is very important because if we know that the process is going to invariant density, it means that usually we observe this process in such a state. So knowing, for example, the stationary density, we are often able to find some parameters of the process. From the biological point of view, it is very important to know exactly, having some experiments to find some parameters. Well, the second property is sweeping. It's in some sense, it looks strange because now the density is going outside any, for example, compact set. So, but it still has some interesting interpretation, as I was trying to say something about it in this epidemiological model. The property of sweeping means that we have permanent the situation when the population will survive. So we will not have still epidemic. So we should go to such a state. It's also interesting in, for example, in a model of cell cycle, it's not positive thing that, but we can have such a property as sweeping, that it means that the cells have a long period of between division. So you can imagine that if we have some tissue and the cells stop to divide, they simply die. So we should be able to check in which condition cellular population is able to survive or not. So this is a very important question. And our aim is to create some tools in, say, theory of stochastic semi-groups that will be able to answer for these questions. So it's a, and I presented some results connected with asymptotic decomposition of stochastic semigroup, with some asymptotic stability, sweeping, and so on. So it was our aim. It is very interesting how it is go up for another, say, kind of semi-groups. It is possible to generalize these notions. In our case, we are consider a very, very special semi-groups, but you can consider one parameter semi-groups on any space, not only in L1. So if this space will be a metric space, we can talk about some stability and so on. So it's an interesting thing how to generalize such a result or find another result on such decomposition. So it's a, in my opinion, is an interesting subject for future study. Well, so we have time for questions, remarks, and so on.
Professor Rudnitsky, very interesting colloquium. I enjoy all talks. Are you getting me?
Yeah, I hear.
Okay, so I enjoy all talks of this colloquium. I would like to revert back to the stochastic operator, the definition you gave. In this definition, the norm of P should be less than 1.
Substochastic, yes, yes.
Yeah. And do you have any interpretation?
Yes,
that?
yes. For example, if you have a diffusion process, then some particles can be out of the system and go out of the system. Then you lost the mass. So in all processes, when you lost a mass, there are a lot of them, then you have a substochastic semigroup.
Okay.
So the stochastic semigroups are for processes when we have preservation of the law, that something should be not changing in time.
Okay.
Can I? First of all, also, I want to thank you to Richard for a really nice colloquium he prepared for us. And also I want to address to Agnieszka and to tell her, I hope I in the correct way pronounce her name, and to tell her that the picture he showed us at the beginning of her talk is actually very similar to the picture from our faculty, from the window of our faculty. So from some point of view, it is almost you are here or we are there. So my question or not question, it is just like a consideration. We have some kind of microphone. I will ask my supporting team to intervene. So I'm in abstract semigroups theory. So I can only think from I'm trained to think in this way, and my whatever questions or can follow this abstract way of thinking. And again, maybe I am, as some of our colleagues thought, naive, but elements of semigroups. I'm thinking about elements of semigroups you mentioned. whether there is some mutual connection between them, whether they are idempotents, for example, or not, whether because if there are, for a semigroup theory, for describing semigroups, it is sometimes, not sometimes, often very important how some of elements react in connection to the semigroup operation. So that is my question, whether there is, for example, idempotents, whether there are regular elements, inverses, something like that. Is it interesting from application point of view?
Yeah.
To include this to mix just abstract theory with concrete elements and concrete situation.
So your question is?
No, it is just
it is only some remark.
Yeah, some remarks. Maybe to think about this for future, future talks, and in changing our scientific experience. At least that is why we are together. We who developed semigroup theory from one side, and you colleagues who apply that. So just to share for the benefit, in order to have both of us to have benefit. We talk about this a little bit on our conference dinner, right? Just remark.
Yeah, I can comment on this.
There are any remarks?
Yeah, you know, there is algebraic structures underlying evolution equations. And we can refer to the works by the group of Sokolov, Leningrad, St. Petersburg schools. So it is evident that under the stochastic evolution equation, there are algebraic structures. And manipulating these algebraic structures, we can show some properties like described by Professor Mitrović.
Yeah.
There are many references to that.
For example, in Agnieszka talk, she said a lot about Hermander condition. For example, it is typical algebraic tool. Is not differential. Of course, you use some brackets in the space of function, but it's rather commutator and so on, such a thing. So there are a lot of different algebraic tools also can be applied to such phenomena. So it's a mixture of science. Mathematics is a mixture of many different sciences. Well, so we will go to the end of the conference probably.
Yeah, and Professor M.N.Hounkonnou can take his position.
Yeah.
And chair the closing ceremony.
Thank you very much, Professor Mitrović. Maybe you will start by some wordings.
Yeah, thank you very much. I want to thank to all our participants, to those from general section, to colleagues, our colleagues, Marcel Tennessee, Paolo Aliano and Richard, who really prepared, who first accept to prepare a colloquium, then prepare excellent talks within colloquium. I'm going to ask them to convey our thanks to the speakers who are not present here. To those who are present here, also I want to thank. I also want special thanks for all those who try to bring from Poland part of niche to us and part of your country. This is maybe important, maybe not, but I told to Professor Richard that unfortunately the Poland is the only Slavic country I never ever visited till now, the only one. So I do hope that this will change very soon, as I hope that our next second edition of this series, Algebra Without Borders, of our first branch, will be in niche in year 2, but alive. In my name, and I think that Academician M.N.Hounkonnou will agree that as soon as everything will more or less safe, we will organize this such kind of meeting live in niche. There also I want to convey a special thanks to our colleague, to my colleague, Professor Igor Dolinka, who strongly support organization of this conference and helped me a lot since Norbert and I 2 years ago announced this conference. And in the end, let me finish with some citation about field, about our series, about world, about scientific branch, which at least put us together, about algebra. It is John Derbyshire, and part of which is written in his book Unknown Quantity: A Real and Imaginary History of Algebra, Joseph Henry Press from 2006. Believe me or not, I never ever read something more beautiful about algebra, and at least I wish I'm capable to put my love to algebra in the way John Derbyshire did. So here is a citation. In our own time, algebra has become the most rare field and demanding of all mental disciplines, whose objects are abstractions of abstractions of abstractions, yet whose results have a power and beauty that are too little known outside the world of professional mathematicians. Most amazing, most mysterious of all, these ethereal mental objects seem to contain within their nested abstractions the deepest, most fundamental secrets of the physical world. And with this, I send you all my best regards from Niche, from, how to say, supporting team. They used to call them M.F.M.N. supporting team, which means mechanical engineering, M.Mitrović supporting team. So regards from them, and we are here.
Thank you very much.
Thank you.
Thank you very much. Flowing Professor Mitrović, I think, and you certainly will agree with me, our objective in organizing this first edition of our conference series, Algebras Without Borders, Classical and Constructive Semi-Groups and Applications, split in general sessions and colloquiums on applications with cognitive sciences, and linguistics, logics, and sciences is attained thanks to the high quality of invited and contributed talks and rich discussion by such an international team of top leading field speakers you form. We spent together nice time, and most importantly, we overcame and broke the barriers between various algebraic structures and connected disciplines. We feel now close to each other in thinking and doing, improving by this way our being and living together. We set the foundations for interdisciplinarity, for a better future for algebras without borders, the backbone of contemporary mathematics. The main task in forthcoming months remains to prepare all needed materials for the conference book to be published by Springer. And to achieve this, we're wondering to invite you to kindly and with the same enthusiasm write your contributing chapters and send us by the end of November. We will share soon the template with you. Dear colleagues, the success of this conference naturally suggests its continuations on a periodic basis, like said Professor Mitrović. So with care, we agree with that and are already in the dynamics of the second edition. We are convinced you are in the same spirit and ready to embark in this exciting adventure inspired by the success of this conference itself. In this expectation, on behalf of the International Organizing and Program Committee members, I'd like to thank everyone for active participation to this wonderful virtual and in-person first edition of our conference series, Algebras Without Borders. Further, on behalf of the organizing committee, I say many thanks to all our eminent scientists who accepted to be member of the program committee. Finally, allow me to present all our gratitude and congratulations to the members of the local organizing committee, in niche chaired by Professor M.Mitrović, who did a splendid job by preparing and warranting all technical dimensions for the success of our conference. They deserve all our gratitude and congratulations and applause.
With me today, the youngest of our team, Nicola.
Nicola and all others. Please, let's applaud them.
Thank you.
We expect to be all able to attend in person the next edition of this conference series in your great city, the city of our dreams. So, goodbye to everyone. With our best regards, thank you for your kind.
And see you soon. Bye from Niš. Regards from Niš.
Bye-bye. See you sometimes in the future.
Yeah, as soon as possible, I hope.
Yeah. Well, it's eventually. Bye-bye.
Bye. Bye-bye.
Bye.
Bye.
Bye-bye, and thank you very much.
Bye, Maria.
Next time, see you.
See you soon alive, Michaela.
Thank you.
Hopefully we'll manage to meet.
Yeah, as soon as possible with all of you.
Definitely.
Bye.
We'll keep in touch anyway.
Of course.
Yeah. Bye.
Congratulations for a good talk, Marian.
Well, thank you very much. we have to talk about the talk. Yeah.
Yeah. We will. We will certainly will.
Yeah, there are still problems which can be dealt with.
Elaborated further.
And I hope we will meet soon, very soon.
Yeah, sure. And
Yeah, so many interesting things to do together.
yes, of course.
To finish what we started and to start with new.
To make progress.
Of course. Yes, of course.
Yeah, make progress.
And thanks again for giving me the opportunity to participate, and
You're welcome.
my pleasure.
Always.
Okay, right.
Bye.
Bye. Bye.
Okay. Bye.
Bye.
It's time for the curtain to fall down. It's time.
Yeah. Okay. Bye. Everyone.
Bye.
Bye.